ನೋಟ್ ಅಲ್ಲಿ ಓದಿ ನೋಡಿ.
Hello, can you hear me?
Yes, sir.
So, can I share my screen?
It is already visible. We are going to start the session in a few minutes. So
No, I would like to share my screen.
yeah, sure,
How
sure.
should I? So how should I do that?
Just a second, sir. Sir, we are letting you know. Just wait a minute. Sir is telling you how to share your screen.
Yeah, I need to share my screen.
Yeah, he will help you. Just a minute. He will join there and help you.
Oh, you need to stop your presentation. Then maybe I will be able to do that.
Yeah.
Sir, 1 minute, sir. Sir, 1 minute.
So can you see my screen?
Yes, sir. It is visible.
You can see my slides?
Yes, sir.
And let me do the full screen and you should tell me whether it is visible or not.
Yes, sir. Yes, sir. It's
So
clearly
is it?
visible. Yes, sir.
And now I'm changing the slide.
Yes, sir. I
It's
can
Is
okay.
see
changing?
the changes. Yes, sir. It's fine.
Yeah. So if you see any problem that if my slides are not changing,
Okay.
then I think Madam has my WhatsApp number. So you can give me a call because I will not be able to see you guys.
Okay, sir.
And I'll not be able to track whether my screen has been paused or whether you can listen to me or whether I have lost the connection.
No problem, sir. We'll let you know.
Yeah.
Thank you.
Hello, good morning. So good morning to the speakers, faculties and all participants. Can you hear me? Is it audible?
Yes, ma'am. I can hear you. Good morning.
Okay.
Yes, yes.
I'm saying good night for me.
Yes, sir. Yes, sir. So, dear participants, today we are in the third day of our webinar, and for today we have three talks. First talk by Professor Sanjeev Kumar Agrawala sir. Professor Sanjeev Kumar Agrawala sir. Sir will be talking about imaging the deep earth with neutrinos. And the second talk is by Professor Bibhudatta Rao sir, that is on emerging ion beams for synthesis of cosmic dust, analogs and testing of radiation tolerance of space photovoltaic cells. And the third talk will be by Pratap Kumar Sahu sir from Niger, Bhubaneswar, that is on the topic lotus leaf effect in ion beam synthesized quantum nanomaterials. So I request all participants to interact with the speakers during the presentation through the chat box. And for a brief introduction about the speaker, I request Prachi madam to chair the session.
Thank you, madam. Good morning, everyone. We welcome you all to the third day of our webinar. We are pleased to have our first speaker, Professor Sanjeev Kumar Agrawala, an Associate Professor in Institute of Physics, Bhubaneswar, as well as in the University of Wisconsin-Madison, USA. He has been an active contributor to the field of high-energy physics. To list a few of those are the neutrino oscillation phenomenology, neutrino astronomy, neutrino geophysics on the Earth matter profile, neutrino event generator GENI, and detector simulations, etc. With regard to his contribution, he has been conferred with several notable awards and grants like Fulbright Nehru Academic and Professional Excellence Fellowship, N.S. Satyamurthy Memorial Award 2020 by the Indian Physics Association, Department of Science and Technology, DST, Swarna Jayanti Fellowship in the year 2019-20, Young Scientist Research Grant for 3 years from 2018 to 2021 from Indian National Science Academy, INSA. Moreover, he has been featured in the Coffee Table book titled 50 Scientists Under 50 as a part of the Golden Jubilee celebration of the Department of Science and Technology, DST, Government of India. Now, I would like to welcome Professor Agrawala to share his knowledge with us. Sir, please.
I hope you can hear me well.
Yes, sir.
So thanks for this broad introduction. I don't think that it was, I think it was not needed. But anyway, I would like to thank the organizer for having this 3 or 4 days of physics program. And I'm sure that there are many speakers, very good speakers gave talk, and students and faculties, they must have got benefited listening to them. So I'd like to thank for the invitation. Now, let me share my screen. And since I am giving a remote talk, so there can be technical glitches. So if you can't hear me, or if you see that my slides are not changing, please interrupt me or just send me a call over my WhatsApp so that we don't lose time.
Yes, yes.
So
Sir, your voice
let
is
me.
very clear. Yes, sir, your
Okay,
voice
great.
is very clear.
Yeah. So let me first share my screen. So and I am doing full screen, and you let me know whether you can see my screen clearly.
Yes, sir, it's visible here.
And I'm changing my slides, right?
Yes, sir. We can see the visible changes.
Okay, great. Okay, slides are getting changed, right?
Yes, sir. Yes, sir.
Okay, great.
It's perfectly fine.
So, okay, it is good morning for all of you. And it is like 10 o'clock in the night here at Madison. But I'm happy to connect with you and share what we are doing here. So the title of my talk is Imaging the Deep Earth with Neutrinos. So in my talk, there are few components which are very essential. And I will try, as much as I can share with you over the next 1 hour or 1 hour or so. So as the title suggests, our goal is that can we use these fundamental particles called neutrinos to learn about the internal structure of our own planet Earth, and let us see whether these neutrinos can provide some important information about the internal structure and composition of the Earth. So let me tell you that this is a very emerging field of science, neutrino science, which has gained momentum over the last 2 to 3 years. And I will tell you why people are thinking that neutrinos can help us to probe our own planet Earth and what is happening in this field. And I'm very happy to share with you that our neutrino group at Institute of Physics has been playing a major role on this topic. And I'm here at UW-Madison, which is the main data center of the IceCube experiment at the South Pole. So here our job is, from the data that IceCube Neutrino Observatory is collecting, the atmospheric neutrino data, how much information they can really reveal about our own planet Earth. So this is the motivation. So I will try to convince you through my talk that neutrinos, when it was proposed by Professor Pauli, he mentioned that I have done a terrible thing. I am proposing a particle which will never be detected. But now, you see, after almost 90 years, not only we have detected neutrinos, we have explored their fundamental properties, and now we are in fact at a stage that we can use these neutrinos to probe our own Earth. So in some sense, it was really good that Professor Pauli was wrong, though he postulated this fundamental particle, but he was wrong, and the neutrino science made a tremendous progress, and now we are at this stage. So I'm changing my slide. So when we talk about the interior of Earth, it has been a long-standing puzzle that what lies inside our Earth. And an active research is going on in this direction. I will just try to give you some flavor what is happening on various fronts. But you can imagine that on the left, I'm showing you a cartoon of our Earth with several layers. And in the below, I'm showing you a plot that I will describe in a moment. So the regions deep below the Earth's surface are inaccessible. And there is no surprise that it is inaccessible because we have large temperatures, pressures, and extreme environments when we go deep inside the Earth. And that is why we don't have any direct access to our inside our Earth. So far, we have gained information about the interior of Earth indirectly using two methods. The first one, you can see my cursor, using gravitational measurements. Another probe is seismic studies. Now, when I will describe one by one how much information we have obtained from gravitational measurements, how much from seismic studies, But on the left at the bottom, I am showing you the depth of the earth. You can see that it is going from 0 to 6,371 kilometer. And when we say seismic studies, so when we have earthquake, then various seismic waves, they propagate inside the earth from the epicenter of the earthquake. And in this plot, what I'm showing you, the velocity of these various waves. There are two types of waves. One is S wave, the shear wave, and another. And here in this plot, you can see the density of the earth at various layers. So you have your mantle, then you have your lower mantle and upper mantle. Sometime, the outer mantle is also, some part of it is known as crust. Then you have the liquid outer core, and then we have solid inner core. And you can see here that the density, how much the density we have from the seismic and gravitational studies, whatever we know, how much density we have. And this density is given by density of the inside the earth. And these blue lines shows you the velocity of the P waves inside the earth. And this green line shows you the velocity of the S wave inside the earth. Now you can see that inside the liquid outer core, there is no green line. That means S wave can't propagate through the liquid outer core. And I will explain in a minute what is the reason behind that. So recently, we have realized that neutrinos can also give you very important information about the interiors of our Earth. Why? Because we know that neutrinos are very weakly interacting particles. They only take part in weak interaction. So the mean free path of neutrinos are so large that they can penetrate anything. So when you observe atmospheric neutrinos, which are coming from the atmosphere around us, and when they pass through Earth and reach to our detector, they can bring information about the interiors of Earth when they reach our detector. Okay? So there are two ways neutrinos can help. One is neutrino oscillation tomography. I remember a few years back, I gave a talk in your department on neutrino oscillation. So, and 2015 Physics Nobel Prize was given for the discovery of neutrino oscillation, which suggests that neutrinos have mass. Now, when neutrinos oscillate, then in some form, these neutrinos, they do talk about with the ambient electrons inside the Earth, which we call neutrino oscillation tomography. And it happens when neutrinos are in the MeV GeV range. Okay. So one way that I will explain today, what is this neutrino oscillation tomography and how it can be useful to know some unknowns about our Earth. And if you talk about very high energy neutrinos, like I'm talking about the energy which is beyond the reach of the CERN collider, like TeV, PeV, hundreds of TeV, PeV energy neutrinos, atmospheric neutrinos, then at those energies, these neutrinos get attenuated inside the Earth. So far, I told you that neutrinos can penetrate anything, but it depends on its energy. If neutrinos are very high energetic, then neutrinos can be absorbed inside the Earth, provided their energy is very high. And this is called neutrino absorption tomography. It is only possible with high energy neutrinos. I will not talk much about that, but I just told you about this ice cube neutrino experiment at South Pole, they are very sensitive to these high energy atmospheric neutrinos. So in ice cube experiment, we are using this neutrino absorption tomography to probe our Earth, but they can also see low energy atmospheric neutrinos, and there we are using the oscillation phenomena of neutrinos to probe our Earth. Okay, so now I'm going to my second slide. I hope you can see my slide change. So in the middle, you have this Earth. Now, when you think about gravitational measurements, when you use gravitational interactions of matter inside the Earth, then it provides the information about total mass and the moment of inertia of the Earth. So how much mass you have inside the Earth and what is its moment of inertia, these two quantities are quite accurately measured using gravitational measurements. So you see, there we use gravitational interaction. I just told you that geophysicist, it is also a very interesting topic of research. Our friends, our geophysicists, they use seismic waves, which came into the, which are originated during earthquake from the epicenter, and they start propagating inside the Earth. I just told you about this S wave, P waves, and these seismic waves from earthquakes, they use electromagnetic interaction of matter inside Earth to tell us about various properties of Earth. Now, what today I am telling you that look, we have these fundamental particles called neutrinos, and we can use atmospheric neutrinos at higher energies. When they get absorbed inside the Earth, through their absorption, you can also probe the properties of Earth. And when you have low energy neutrinos in the sub-GeV, multi-GeV range, then when you observe that neutrinos oscillate, during their oscillation, they become sensitive to the Earth's matter because they pass through deep inside the Earth. And then you can use this neutrino oscillation tomography to also penetrate or also probe our planet Earth. So you can see that here I am proposing a multi-messenger tomography of Earth using all the three fundamental interactions that you can think of: gravitational interaction, electromagnetic interaction, and now neutrinos with their weak interactions. So the idea that is developing over the last few years, that can we combine these neutrino data from various oscillation experiments with seismic and gravitational data, and can we probe our Earth better? And this is what we call multi-messenger tomography of Earth. This is a very emerging field of research, and IOP is playing a leading role in this hot topic. So I hope I just changed my slide. I will briefly talk about gravitational measurements. So I told you that from gravitational measurements, we exploit gravitational interaction to measure the properties of Earth. Now, we know from gravitational measurements, the mass of the Earth is quite well known, and this is the value. And we know what is the radius of Earth. Now, if you just divide this mass over the volume, you can see that the average density inside the Earth should be around 5.5 gram per centimeter cube. Clear? But you know, if you just dig the Earth and if you see the ordinary rock, the density of the ordinary rock is 2.8 gram per centimeter cube, roughly. Then it immediately tells you that there must be some density near the center of Earth, which should be higher than 5.5 gram per centimeter cube, right? Because if Earth would have been having a uniform density, then everywhere the density will be 5.5 gram per centimeter cube. But you know, around the crust, the density is around 2.8 gram per centimeter cube. So far, whatever instruments we have been able to dig up to 10 kilometer or so. And we have seen this kind of densities. So then, to compensate the total mass, you can imagine that there must be a very high dense region around the center of the Earth. So in this way, from gravitational studies, you can infer that there must be a dense core at the center of the Earth. Another is the moment of inertia. Now, if our Earth would have been a uniform sphere, then from this simple relation, the moment of inertia would have been 0.4. But the measured amount of moment of inertia is 0.33, slightly less compared to 0.4. So since the measured moment of inertia is less than the expected, it tells you that our Earth is not a uniform sphere, and definitely more matter is concentrated near the axis of rotation. So I'm just giving you a very simple idea that from these basic measurements, you can infer that there is some dense region at the center of the Earth exists. There is a core. But this much, we can't say anything beyond that, that at which position your core starts, what is exactly the density inside the core, what is the chemical composition that we have inside the core. Gravitational measurements can't tell you about those information. Okay, now let me move. Now I will talk about seismic measurements. I hope you can see my new slide, right? So I told you that when we have earthquakes, we have these seismic waves, and we exploit the electromagnetic interaction of matter inside the Earth. So there are two seismic waves, two types of seismic waves. One is called S wave, which is called known as shear wave. This is slower compared to P wave. This is known as pressure waves. Now we have this empirical relation which tells you how the velocity of this shear and pressure waves looks like. Now please look at these two expressions. When you talk about shear waves, this is given by the square root of mu over rho. Now what is mu? Mu is the shear modulus and rho is the density of the material. But when you talk about pressure waves, apart from your shear modulus and the density, you also have bulk modulus. Okay. Now you can see here for the P waves, since it depends on both shear modulus and bulk modulus, and therefore it can pass through the outer core, which is solid in nature, because if your outer core is liquid, then for liquid, your mu, the shear modulus is 0. And if mu is 0, then the velocity of the S wave in the outer core is basically 0. And this tells you that your outer core is liquid in nature. So I hope I have been able to convince you that how seismic waves tells you that this outer core should be liquid in nature, because these S waves, they don't penetrate through outer core because of this reason. Because if it is liquid in nature, then this mu is 0. That means there is no shear modulus for liquid, and this S wave can't propagate through that. But since you have this P wave, which also depends on this bulk modulus, which is non-zero for liquid. That is why you have a finite velocity of the pressure waves through outer core. So pressure waves can go through both inner and outer core. So I'm just giving you a flavor that how by exploiting the propagation of these seismic waves, you can get knowledge about the nature of various parts of the earth, that whether it is solid, whether it is molten, whether it is liquid, whether it is like, neither solid nor liquid, this kind of information, and also some idea about the density through which this wave propagates. Because you see, velocity depends on density. So I'm just giving a rough idea that how exploiting the seismic waves, our geophysicist friends, they tell us various properties of our earth. Okay. Now, let me switch my talk to neutrinos because we work with neutrinos. So can you see my slides? This slide on neutrinos in the standard model of
Yes.
particle physics?
Yes, sir.
Good. So here I'm just showing you our standard model of particle physics. So what you have on the left, you have these leptons and quarks. Now these neutrinos belongs to neutral lepton family. So as far as active neutrinos are concerned, we have three different type of neutrinos: electron type neutrino, muon type neutrino, and tau type neutrino. Now, when I say active, it means they take part in weak interaction. What does that mean? It means that they can interact with these W and Z bosons because these are the gauge bosons which are responsible for weak interaction. So these neutrinos, they only talk to these W and Z bosons. Therefore, these neutrinos only take part in weak interactions. They don't talk to gluons or photons. And in fact, we don't know how these neutrinos get their mass. We know that Higgs boson is responsible to give mass to other fundamental particles, but somehow that mechanism, is not at work when we think about neutrinos, because in the basic standard model of particle physics, neutrinos are massless. And I will talk about that. So I'm just giving you a flavor that in this picture, why these neutrinos are so special. First of all, they have zero charge. They are neutral. And you know that if some particles are neutral, then they will not interact electromagnetically. So it will be very difficult to detect them. Now, if you see the mass of all these particles, can you see it is written? The mass of all these fundamental particles are written in their boxes. So if you compare an electron and an electron type neutrino, from the present data, I can tell you that the mass of neutrinos are almost 6 orders of magnitude lower than electron, its charge cousin. Now you can ask me, why this is so? Why neutrinos are they have so less mass? And this is an open question. We have some ideas that why neutrinos have so tiny mass as compared to their charge cousin like electron, muon, or tau. But we don't have a clear picture yet. Okay. And also, why neutrinos only take part in weak interaction? I can only say that this is our experimental evidence. So far, all the experiments suggest that neutrinos only take part in weak interaction and they violate parity. Okay. So in many ways, neutrinos are special. But today, I will tell you, they are becoming more special now because they can also tell you about your own planet Earth, where we exist, where we stay. How? Let's see. So I told you that we have three active neutrinos, nu e, nu mu, nu tau. So we have three different flavors of neutrinos. So when neutrinos are produced, they are produced in flavor eigenstate. And when you detect, when they are also detected in flavor eigenstate, but when they propagate from source to detector, they propagate in their mass basis. And I will talk about that when I will describe the oscillation phenomena briefly. So since neutrinos are neutral, no way you can detect them directly. So then you can ask me, how can I confirm that I have seen an electron neutrino or a muon neutrino? Suppose you have a detector. A detector can be of some liquid, some iron, some argon, or some scintillator, any material, any material. You just need huge detector where you have electrons, protons, and neutrons. Now, when these neutrinos come, they interact weakly with the ambient particles that you have inside the detector. And they produce their charge cousin. So if an electron neutrino will come, then through interaction, they will create an electron inside the detector. A nu mu will create a muon, and a nu tau will create a tau particle. Now, interestingly, you observe that these are charged leptons. They are charged particles. So you can detect them. We know how to detect charged particles. So the take-home message that Pauli proposed neutrinos in 1930, and he said that we will not be able to detect these guys. And it took us almost 26 years. In 1956, we first detected the neutrino electron antineutrinos from reactors. So it took us almost 26 years. And only lately, over the last 2 decades, our experiments have become so big and precise that we have been able to see neutrinos from all possible sources. So you should take home one important message, that neutrino detection is a very tough job because they are neutral particles. Also, we have antineutrinos. When we talk about atmospheric neutrinos, we have mainly muon type neutrino. Then also we have electron neutrino, and also they are antiparticles. If you have antineutrinos, then you will have positron, anti-muon, or anti-tau here. Okay, so this is the way we detect them. Now, when I am trying to convince you that I will probe the properties of Earth, my best bet is atmospheric neutrinos. Why? They are free. They are produced in atmosphere when cosmic ray particles, basically primary protons, they interact with the air shower, air nuclei. Then they produce lots of pions and kaons. And these pions are short-lived particles. I am assuming that you are all familiar with pion decay. It's a two-body decay. So pion will immediately decay to a muon type neutrino and a muon, and this muon will further decay to a muon type antineutrino and electron type neutrino. So you can see from this decay chain that in our atmosphere, we have 2 muon type neutrinos and 1 electron type neutrinos. Just do not give too much importance on their charge, like it is particle, it is antiparticle, but you can immediately see that in the atmosphere, we have like this muon neutrino flux is twice than this electron neutrino flux. Because of this, like we have 2 nu mu and nu mu bar, and we have 1 electron type neutrino. Another important property of atmospheric neutrinos is whether these neutrinos are coming from the top atmosphere or whether they are coming from below, passing through the Earth. If there are no oscillation, you expect that equal amount of neutrinos will reach at your detector. So on the right, I am showing you how the atmospheric neutrino flux behaves as a function of energy. So you see that these atmospheric neutrinos follow a power law. It varies as e to the power minus 2.7. And for this reason, you see when you go to higher energies, the atmospheric neutrino flux falls very sharply. But this flux is almost isotropic. It is up-down symmetric. I just told you that. And we know the flavor composition, that from atmospheric neutrinos, we will expect 2 nu mu or nu mu and nu mu bar, muon type neutrino, and 1 electron type neutrino. So the flavor composition is also very well known. And we have their antiparticles. Okay. And another beauty of atmospheric neutrinos is that you get atmospheric neutrinos over a wide range of energy. You can see here in the x-axis. So that is why in ice cube experiment, when they see high energy neutrinos, you can see my cursor, they use neutrino absorption. When neutrinos are very high energetic, they can't pass through Earth, they get stopped. And how much neutrinos will be stopped depends on how much matter you have inside the Earth. In that way, they bring information about the Earth composition. And when you see these low energy neutrinos, when they oscillate basically, they also feel Earth's matter effect. And this is the heart at neutrino oscillation tomography. So these atmospheric neutrinos can help you to probe the properties of Earth using their absorption at higher energies and oscillation at lower energies. Now let me go to my next slide. So there are many experiments which are taking atmospheric neutrino data. The main candidate is Super Kamiokande. You all are familiar that 2015 Nobel Prize was given to Professor Takaki Kajita, who is the spokesperson of Super Kamiokande experiment. He played the important role to discover neutrino oscillation by seeing the zenith angle dependence of atmospheric neutrinos. And this experiment is still running. Now the good news is that Japan is on the way to making an even larger detector called Hyper Kamiokande, and it will be operational by 2027. It is 8 times bigger detector. Okay. Then in the Mediterranean Sea, people also have detector inside the sea, and this is called KM3 net. So they have some strings with photomultiplier tubes, and they have put those strings inside the sea. So your whole sea becomes the detector. And this is called KM3 net and Orca. You can see the size. The size of the detector is 6 megaton. So you are basically using natural sea water as a detector. Then we have this ice cube at the South Pole. So you can see the imagination of the scientist. They have gone to South Pole at Antarctica. They have digged the ice in a region 1 kilometer cube region, and they have put photomultiplier tubes. And now they are using ice as their detector. When neutrinos will come, they will interact with the protons, neutrons, or electrons inside the ice. And then they will produce their charge particle. And with these photomultiplier tubes, you will see their signature of the charge particles. So the low energy part of the ice cube is called deep core. And our group is now analyzing the data of this deep core experiment. They have 10 years of huge amount of data. And for last 8 months, me and my group, we are analyzing their data to see what information can they tell us about our own planet Earth. In Fermilab in US, they are building another detector called Dune. It's a proposed 40 kiloton liquid argon detector. and they will also observe huge amount of atmospheric neutrinos. And when I talk about absorption, I told you that we need to rely on the high energy atmospheric neutrinos. You can see this green circle. These high energy neutrinos will be absorbed in these big detectors inside ice cube or in Lake Baikal or in Mediterranean Sea called Chem3net. And when they will be absorbed, then we will be able to know how much matter they have faced inside the earth when they get absorbed. Okay, so this is the idea. So we are going through a very interesting time where there are so many experiments which are taking data. They are collecting atmospheric neutrino data. In next 5-10 years, there will be even more bigger experiments are coming. So I just want to tell you, this young audience, that there are a lot of scope of doing fundamental science when this detector will come online. They will have huge amount of atmospheric neutrino data. And believe me, within next 10-15 years, neutrinos will become a key player to probe our own Earth through their interesting properties. But just the science has just started, okay? But it is important that we should be familiar what is happening around. Okay, so let me just tell you briefly about neutrino oscillation. So over the last 20 years, I already discussed that few years back when I was there in your department about neutrino oscillation. So there are many pioneering experiments, have taken neutrino oscillation data over the last 20 years. And these are some names of the experiment. So in these experiments, we have detected solar neutrinos, neutrinos from atmosphere, neutrinos from our reactor, and also man-made accelerator neutrinos. But when we detected those neutrinos, we found that the amount of neutrinos that we detected and the amount of neutrinos which were produced, they are not same. Means some of the neutrinos, they have oscillated to a different flavor, and that is why you can't see them in your detector. So all the data from these experiments, various experiments, not only one, there are plethora of experiments here. When we saw the data, when we analyzed the data from these experiments, from various sources, sometimes the source is sun, sometimes the source is atmosphere. And you remember, the energy of these neutrinos are vastly different. The neutrinos from sun, they have MeV energies. But neutrinos from atmosphere, they are mostly at GeV energies. So they have different energies. And also the length that they travel is also different. But one thing is common. When you analyze their data, they all suggest that neutrinos change their flavor when they move in space and time. And this is called the phenomenon of neutrino oscillation. Now I have changed my slide. You can ask me, why so much excitement about neutrinos? The reason is, we have seen that neutrinos oscillate. But neutrinos can only oscillate if they have non-zero mass, and they should mix with each other. But the standard model of particle physics, which have been developed over the last 60 years, it suggests that neutrinos are massless. Why? Because in experiments, we have found that neutrinos are only left-handed particles. There are no right-handed neutrinos, and all the antineutrinos are right-handed. There are no left-handed antineutrinos. Now, what is this left-handed, right-handed? Suppose you assume a particle, and if the direction of its spin is along the direction of its momentum, then we call it a right-handed particle. And if the direction of the spin of that particle is opposite to the direction of its momentum, then we call it left-handed particle. So the experiment suggests, again, this is purely experiment. Experiment suggests that all the neutrinos that we have observed, they are left-handed, and all the antineutrinos are right-handed. Now, in the standard model of particle physics, when we write a mass term for a fundamental particle, we need both left-handed particle and also the right-handed component. So we need both left-handed component and a right-handed component. Just think like you have a beam of electrons. If you have a beam of electrons, in that beam, you have 50% right-handed electron, 50% left-handed electron. So since electrons are both left-handed and right-handed, you can write a mass term for electrons. But when you think about neutrinos, and if you see a neutrino beam, then 99.9999% these neutrinos are left-handed. So there are no right-handed neutrinos. And that is why you can't write a mass term in the basic standard model of particle physics. So you see, there is a clear conflict between what data is telling and what your theory or the model is telling. So the neutrino oscillation has been established now. We have seen the signature of neutrino oscillation in almost all the experiments over the last 2 decades. So this data tells you, this neutrino oscillation data, it tells you that our standard model of particle physics is incomplete. We need to extend the standard model of particle physics so then we can accommodate this non-zero neutrino mass so that we can explain neutrino oscillation. So I hope I could convince you, because of this oscillation property of neutrinos, they have become so interesting in the field of particle physics. Now, for this reason, in 2015, Nobel Prize was given to Professor Arthur MacDonald. They solved with the SNOS experiment, the solar neutrino puzzle, and Professor Kajita-san, using the super Kamiokande experiment, they solved the atmospheric neutrino puzzle. What was the puzzle? That half of the muon type neutrinos, they were lost. Actually, what was happening, that half of the muon type neutrinos were oscillating to tau type neutrinos, and super Kamiokande is not very sensitive to tau type neutrinos. So ultimately, they could prove that this is because of neutrino oscillation. And similarly, in SNO experiment, they also proved that the amount of half of the solar electron type neutrinos were oscillating to muon or tau type neutrinos. And that was the reason behind solar neutrino anomaly. And 2015 Nobel Prize was given to these 2 brilliant physicists. Now, what is neutrino oscillation in a nutshell? That I told you that neutrinos are produced in weak interaction in the flavor states, but when they propagate in the mass eigenstates. And these flavor eigenstates are the linear superposition of these mass eigenstates. And these flavor and mass eigenstates are connected by a simple 2 cross 2 unitary neutrino mixing matrix. I'm talking about only 2 flavor now. Now, without going into details, just think about, if suppose you have 2 neutrino mass eigenstates, nu1 and nu2, with different masses m1 and m2, since their masses are different, they will take different amount of time to reach the same point. Since the time taken by them will be different to reach the same position, there will be a phase difference. And when you have a phase difference, you know from Young's double slit experiment that there will be interference. Now, to make it more clear, we have all read in quantum mechanics, there is a concept of wave-particle duality. Sometimes you can treat a particle as a particle, sometimes you can treat as a wave. So the mass of the particle determines the frequency of the wave. So you can think of that these neutrinos, these electron, muon, and tau type neutrinos, they are actually the mixtures of multiple waves with different frequencies. Because I told you, if you consider them as a particle, then they have different mass. But if you consider them as a wave, then they have different frequencies. Now, this is a simple example. Suppose you have a wave 1 with a frequency x, and another wave with a frequency y, and if they superimpose on top of each other, you can see this interference pattern, right? So this is exactly the phenomena of neutrino oscillation. Now, I don't have time, so I will not go in detail. So when you talk about neutrino oscillation, we have these two fundamental parameters that we want to measure. One is called the mixing angle, which governs the height of the oscillation. And this is the mass square difference. This is the mass square difference between M1 and M2 or M2 or M3. This is called the frequency of the oscillation. So the job of all these oscillation experiment is that you collect more and more data, analyze the data, and then try to measure this fundamental quantity, this mixing angle, and this mass square difference. And this oscillation depends on neutrino energy and the amount of distance they have traveled. So this is driven by L by E. So it's a L by E phenomena. It's a sinusoidal function of L over E. And you can see this is the oscillation pattern that Super Kamiokande detector has seen. And you can see the nice oscillation pattern over there. Okay. So when neutrinos pass through Earth, when their flight distance is more than 1,000 kilometers, half of the nu mu, they oscillate to nu x. And you see that 50% of nu mu are almost lost. That was the reason behind atmospheric neutrino anomaly. Now, when these neutrinos, they oscillate inside the Earth, they also talk to the ambient matter inside the Earth. How? So this is the so-called preliminary reference Earth model of Earth. On the bottom left, you can see this is the density distribution, radial density distribution inside the Earth according to PREM profile. But I want to emphasize that this PREM profile is not a directly measured profile. It has been inferred when you combine the gravitational and seismic measurements. But when neutrinos, they travel through Earth and reach to you at your detector, they can tell you what density profile they have encountered inside the Earth through Earth's matter effect. Okay. So what is Earth's matter effect? So this phenomena was discovered by these three brilliant physicists, Professor Alexei Smirnov, Professor Mikhaev, and Professor Wolfenstein. I had the opportunity to work closely with Professor Smirnov. So they proposed that these neutrino oscillations can dramatically change if they pass through matter. And this is called the Mikhaev-Wolfenstein-Smirnov matter MSW effect. And when neutrinos pass through matter, their oscillation probabilities can be altered depending on how much matter they will face inside the Earth. And if you can measure the oscillation probability well, you can indirectly tell that what was the matter that they have faced when they have oscillated. Okay, so this was proposed by these three physicists, and you can see it is Mikhaev M, S for Smirnov, W for Wolfenstein. This is called MSW effect, following their name. And when in neutrino oscillation, if our data is sensitive to this MSW effect, then you can imagine that it will be sensitive to our Earth. How much matter inside Earth we have, where we have core, where we have mantle, what is the chemical composition, how much electrons, how much proton, neutrons we have. All these things you become sensitive to if you can explore MSW effect or Earth matter effect during neutrino oscillation inside the Earth. Okay, what happens depending on whether you have neutrinos or antineutrinos and how their masses are arranged, if they will feel matter effect, their oscillation can be enhanced or can be decreased. I will give you an example. So what is this matter effect? Little bit more details. When these electron type neutrinos, they pass through Earth, they interact with the ambient electrons, and there is a coherent forward scattering of these neutrinos with the ambient electrons. And this gives us to an additional potential called MSW potential, which is positive for neutrino and negative for antineutrino. And this MSW term, this is the heart at neutrino oscillation tomography. Okay. More precisely we measure this quantity, more precisely we'll be able to probe our Earth. Okay. I'm not going into details because I need to wrap up in next 5 minutes. But just try to understand when I say neutrino oscillation tomography, basically I need to measure this quantity. I need to measure how much Earth's matter effect has been felt by these neutrinos or antineutrinos, and then I will be sensitive to various properties of Earth. Okay, so I'm just giving an example. Suppose you have a neutrino, atmospheric neutrino, which is passing through the core of the Earth. So the distance that these neutrinos are traveling is more than 11,000 kilometers. So we know that our diameter of Earth is around 12,600 kilometers. And suppose an atmospheric neutrino is coming from other side of the atmosphere, and it is passing through the core of the Earth. And suppose the distance that it has traversed is around 11,000 kilometers. Then if you measure the oscillation probability of these neutrinos at various energies, you will see a peak in the oscillation. That means neutrinos will oscillate more. There will be an enhancement in the oscillation. If your neutrinos are in the range of 6 to 12 GeV, or rather 6 to 10 GeV, this will only happen if there is a mantle inside the Earth. If there is no mantle, you will not see this enhancement in the oscillation. Again, you see another peak here, and these are called parametric resonance or neutrino oscillation length resonance. And these peaks, this peak, I'm talking about the second peak. This peak appears in the picture when neutrinos see an abrupt jump in the density. When neutrinos enter into the core from mantle and they again enter into the mantle, when they see a density jump from mantle to core, then you see an enhancement in the oscillation probability, which we call parametric resonance or neutrino oscillation length resonance. Now you see a neutrino is entering into the Earth and going on the other side. So they will enter, they will go through outer mantle, lower mantle, outer core, inner core, then again mantle and core and then mantle. So depending on whether you have a mantle, whether you have a core mantle boundary, you will see these resonances in neutrino oscillation. And when neutrinos pass through core and again reach to mantle, you will see this third resonance. So the summary is, in neutrino oscillation experiments, we have so much data. If we analyze the data, do the Fourier transform of those data, and if we can establish that we have seen this peak, then in other way, we are establishing the profile of the Earth. That look, yes, we have a mantle, we have a core mantle boundary, then we have a core, then again we have a mantle. Okay, so the height of the resonance, these three resonances, and the location of these resonances are basically the handle through which neutrino oscillation becomes sensitive to neutrino Earth's matter and indirectly to our Earth profile. Okay, so remember, we need to see these resonances in neutrino oscillation data, and then we'll be sensitive to our Earth profile. Now, just to convince you, if there is no matter inside the earth, suppose that there is no matter inside the earth, then the oscillation probability, you see this oscillation probability, if there is no matter inside the earth, the oscillation probability will like this green line. If you remove all the matter from the earth, this is the oscillation probability of electron neutrino to muon neutrino, the green line. But if you assume that there is a matter inside the earth following the preliminary reference earth model, then your oscillation pattern will be this black line. Now, if you assume that no, everywhere inside the earth, my matter is uniformly distributed, then the oscillation pattern will be this magenta line. Now you do your experiment and see the oscillation pattern. If it matches with black line, then you establish that yes, my data is telling that I have seen the PREM profile inside the earth. If your data matches with green line, then this will be a surprise. Your data is telling basically that I have not seen any earth matter effect. So I'm just giving a flavor. I'm not going into details. That when we analyze the oscillation data, we need to see these resonances, their peak, their height, and their location. And then we will be sensitive to many issues regarding our Earth. And what are those issues? If we analyze the oscillation data better, we will be able to convince you that there is a Earth inside, there is a matter inside the Earth. We can be able to convince you also that there is a density distribution inside the Earth, so the matter is not uniformly distributed. We can also measure the mass of the Earth. We can also validate there is a core. In fact, last week we posted a paper where we showed that our India-based neutrino observatory, if this experiment will come in next 5-10 years, by observing atmospheric neutrinos, they should be able to tell us where exactly the core mantle boundary is. Okay, and if you await more and accumulate more and more data, you can even sensitive to the chemical composition of core. And these are the open issues. Believe me, these are the open issues, and our geophysicist friends are highly interested if neutrinos can give them some information. Okay, so for this reason, in the month of August, July and August, I organized a workshop at University of Utah. It's called Multi-Messenger Tomography of Earth. So this is the first workshop that we organized where we invited people from neutrino communities and geoscience communities. And we had a 2-day rigorous meeting, and we discussed among ourselves what are the known and unknowns we have about our own planet and how neutrinos can help the gravitational and seismic measurements. We had a nice organizing committee. You can see Professor Amol Dighe from TIFR. And then we have Professor Francis Halgen. He's the spokesperson of IceCube experiment. There are other neutrino friends, geoscience community, friends from geoscience communities. So we had this nice organizing committee. And in that meeting, we could identify what are the big unknowns we have now as far as our Earth is concerned. I will not go through them. I will share my slides and you can read. We also get to know that there are some new structures that we have discovered recently inside the Earth. They are known as large low velocity provinces, LLVPs, and ultra low velocity zones, ULVZs. And it would be very interesting if we can confirm that those regions exist inside the Earth using neutrino oscillation. Okay, so this was the picture taken during the workshop. So this is my conclusion, that we have just started. I'm telling you, the science that I just talked about is a very young science. Like, we are exploring these ideas only in the last few years. So we just started our journey that we can use neutrino oscillation tomography of Earth via Earth's matter effect in atmospheric neutrino oscillation. If you have high energy atmospheric neutrinos, you can use also the absorption of neutrinos to know many things about our Earth. So I want to tell you that now neutrinos are going into a new era where you can have a practical application of neutrinos. Not only they can tell us about the fundamental science, but you can use them to probe many unknowns about our own interior Earth, which we called multi-messenger tomography of Earth. Okay, and there are many experiments which are now taking data. In next 10 years, there will be at least 2 to 3 big experiments are coming. So in next 15 years, I can tell you that this field is going to emerge like anything. So let us stay tuned and see what neutrinos can tell us in next 15 to 20 years about our own planet Earth beyond gravitational and seismic measurements. Thank you.
Thank you, Professor Agarwala, for such an educative presentation on neutrinos. The importance of oscillation property of neutrinos corresponding to their mass and handedness, which make them actually vital in particle physics, is really exciting. The overall explanation about these fundamental neutrino messengers that can be tuned into a new probe to investigate the internal structure and the composition of our own planet was indeed interesting. So we can now take a couple of questions from the audience.
Yes, I could not see the audience. So yes, I would be happy, if students can ask questions, and I will be happy to answer. You can still see my slides, right?
Yes, sir.
Yes, yes. Slides are,
Yeah,
sir, visible, and students are there in the smart room. Our students are there in the smart room, and some more participants, they have joined from different colleges.
Yeah, so please.
And they have put their question in chat box. Madam will read out the questions and please answer.
Sure.
So the first question is, though neutrinos are almost massless, how do they take part in gravitational interaction?
Very good question. So when I said that from gravitational measurements, we know the properties of Earth, their neutrinos didn't play any role, because if you think about total mass of the Earth, okay, then neutrinos are so tiny in mass. In principle, they can have gravitational interaction, but they are not going to play any role in our measurement. Okay, because see, if I give you two balls and I just ask you that calculate the gravitational interaction between these two objects, and if you replace those objects by neutrinos, since their mass is non-zero, they will have some tiny amount of gravitational interaction. It is not zero, but also this is so tiny that they will not be helpful or play any role when you measure the mass of the Earth through gravitational measurements, because there are other fundamental particles which will constitute the mass of the Earth, not the electron, not the neutrinos. Okay. So neutrinos have gravitational interaction, but it is very, very weak because their mass is very tiny.
Okay.
Did I answer the question?
Yes, sir. So the next question is,
maybe students can talk to me directly if they want. This was the question, right? That how they can take part in gravitational measurements, right? That was the question.
yes, sir.
Yes. So I want to reiterate again. Any particle, if it has a mass, no matter what, small, non-zero, whatever, if it has a mass, even the tiny amount, in principle, it has a gravitational interaction. Now the question is, that interaction is how big, how small. And if you just have an idea that neutrino mass is 6 orders of magnitude lower than electron. You know the mass of the electron is half a MeV. And now the data is telling that neutrino mass, even it is less than 1 electron volt. 6 orders of magnitude, 1, 0, 0, 0, 0, 0, 0. So it is so small, but I can tell you that it has very tiny amount of gravitational interaction. It is not 0. It will be 0 if the mass would have been completely 0. Yes.
Thank you, sir. So the next question is, how does the electromagnetic interactions combine with shear waves and pressure waves?
Yeah. So you see, when you talk to your geophysicist friends, the language they speak, they don't speak in this language of electromagnetic interactions, or weak interactions or gravitational interactions. They have their own nomenclature. But it is, you can see that when you have these shear waves or pressure waves, and when they propagate inside the medium, inside the earth, then there will be electromagnetic interactions, right? Because you have this, inside the earth, what you have? You have like, electrons, protons, neutrons, you have charged particles. And when these waves will propagate, there will be electromagnetic interaction, okay? And that is why in particle physics point of view, we call that there will be electromagnetic interaction of these S and P waves.
Okay, sir. The next question is, why do the neutrinos perform oscillations at lower energies and not at higher energies? Do the atmospheric neutrinos come in bunches?
Very good question. So let me just go to one of my plot. So let me answer one by one.
Yes, sir.
Whoever has asked this question, I'm very happy. So this is your atmospheric neutrino flux. So on the right, you can see that what is plotted, the flux of the neutrinos in some unit as a function of energy. Now, you can see that this is continuous. So it is not like, you have atmospheric neutrinos in bunches or packets. If you have an experiment which can detect neutrinos at various energies, then you will see that you will have neutrinos at 1 MeV, 2 MeV, 3 MeV, 4 MeV, 5 MeV. So there will be no gap that, okay, I'm seeing neutrinos only up to 10 MeV, then there is a gap of 20 MeV. No. So the summary is, there is a range of atmospheric neutrinos from few MeV to hundreds of GeV. And in principle, if your detector is sensitive, you should be able to see atmospheric neutrinos at all possible energies. Okay? But it depends on, because you know that neutrinos, they don't interact. But when you look at the atmosphere, neutrinos are coming with all possible energies. But it is up to the probability when they will interact in your detector and you will see an event. That's a different story. But if you just look at the atmosphere now, if you look at the atmosphere outside, or if you look that, there is atmosphere on the other side of the earth, at a given time, atmospheric neutrinos are coming from all possible energies. Okay? So this is your first question. Second, I told you that neutrino oscillation happens when neutrino energies are small. So let us look at this plot. So when neutrinos have energies from few MeV to say tens of GeV, then they oscillate. But when neutrino energies are very high, they don't oscillate. Now, why? What is the reason behind that? So for that, I should take you to this formula. Okay. So neutrino oscillation depends on the energy of the neutrino. You see in this formula, there are product of two sine square function. Now, in nature, we don't know what is the value of this mixing angle theta. We don't know what is the frequency of the oscillation, but we know how much distance neutrinos has traversed and what is their energy. Now, if you take the energy of this neutrino very large, then the oscillation length will be so large that it will not oscillate inside the Earth. So the oscillation length, you can calculate immediately from this expression, what is the oscillation length? One oscillation length. So you see, this is the oscillation length, right? You can imagine that this is the one oscillation length, right? So this oscillation length is proportional to the energy of the neutrino. If you are talking about very high energy neutrinos, the oscillation length is so large that they will not even oscillate inside the entire diameter of the Earth. That means you are not giving enough length these neutrinos to oscillate. But when you go to lower energies, they can oscillate multiple times because the typical oscillation length is small when your energy is small. And that is why you can see that oscillation when neutrinos come to you at your detector passing through the Earth. So the summary is, at higher energies, the oscillation length is very high, and we don't see that oscillation. At lower energies, at MeV GeV energies, the oscillation length is small, and that is why they can oscillate on the way when they come from the source to your detector. Okay? Did I answer your question?
Yes, sir.
Okay.
Then the next question is there a deeper fundamental property of neutrino oscillations? How does it work at the field level?
What level?
Field level.
Field.
Yes.
Okay. So good. So if I understand your question, see, neutrino oscillation has a far-reaching consequence. I tried to convince you that neutrino oscillation is the first exclusive evidence, lab-based evidence. Okay, it is the first particle physics-based evidence that our standard model is not complete. We have some evidence from cosmology, like this dark matter, dark energy, but these are all cosmic observations, not in our lab. And also, standard model cannot explain dark matter and dark energy. But neutrino oscillation is the only phenomena which tells you that your standard model is not complete, because standard model can't predict neutrino mass. And for oscillation, you need mass. So neutrino oscillation has a deeper consequence in particle physics. Now coming back to your second question, what is this connection to field? Now I told you that in quantum mechanics, we have this wave-particle duality. So sometimes you can treat a particle as a particle, sometimes you can treat a particle as a wave. But then to explain the present day particle physics phenomena, we have a concept called quantum field theory. Okay, so if you are familiar with quantum field theory, there we treat this particular wave as a field. When we say Higgs particle, it is not a particle, we treat it as a field. Because why we need to introduce this concept of field? Because in this field theory concept, a particle can be created or a particle can be, destroyed. So to have this phenomena that when two particles collide in CERN and you have two new particles, or when two particles collide, they disappear. So to have this creation and annihilation of particles, you can only explain this when you introduce the concept of field. So quantum field theory is a mathematical language that you must need to explain any phenomena in the modern day particle physics. Okay? And just to give you a small answer, it was mandatory so that you can explain this creation and annihilation of particles. Second, whatever I just talked to you, this quantum neutrino oscillation, it's a pure quantum mechanical phenomena. But if you allow me 1 hour and if you give me a board and chalk, I can explain that if I consider neutrino as a field, then also I can derive the same formula, and that will match with my experimental data. So this neutrino oscillation concept, it is purely quantum mechanical phenomena, but if you treat neutrinos as a field, then also you can explain this neutrino oscillation, okay? And the modern day particle physics tells us that we must consider the concept of field. All the particles are basically field, okay?
Okay, sir. The next question is, how does the oscillation frequency of neutrinos change such that change their flavor? What is the perturbation that change the frequency?
Good. So I told you in my formula that, where the frequency comes, like, in this simple formula, let me just take you there. So this is called the frequency of the oscillation, okay? And now you see that what is this delta m square? Delta m square is the mass square differences. So if you think about nu e and nu mu, two flavor neutrinos, when they propagate in the mass basis, in the mass eigenstate, with a mass eigenstate mu1 and mu2 with mass eigenvalues m1 and m2. Now the first condition is the perturbation. If I understand correctly, the perturbation that you need is that these two masses should not be equal. They has to be non-degenerate. So suppose if one mass is 0, another mass is x, you can still see oscillation. If one mass is x1, another mass is x1 plus epsilon, then also you can see oscillation. So in this way, I can only explain that this is the perturbation. Perturbation means you need two non-degenerate masses. See, if these two mass eigenstates have same eigenvalues, if m1 and m2, if m1 is equal to m2, there will be no oscillation. Why? Because then this quantity is 0. And if it is this is 0, there is no oscillation. So here, I can say that the perturbation is basically that one mass eigenvalue will be different from other mass eigenvalue by small amount. Okay. So okay. I forgot, there was another question, like I addressed this, perturbation thing, but before that there was any question?
Sir, how does the oscillation frequency of the neutrinos change such that they change their flavor? What is the perturbation that change the frequency? It was
okay. So perturbation part I explained, but you see, this frequency is not getting altered. In nature, this parameter has a fixed value. Remember, just think about two flavor oscillation. You are asking that how much electron type neutrino can oscillate to muon type neutrino. And if you write down that expression, this is the expression. And in this expression, this theta, the mixing angle, and this frequency, they are fixed quantity. During oscillation, they don't get changed. During the oscillation, what is changing? Changing is basically this L, okay? Because they are coming from the source to detector, and this baseline is changing. Energy is also fixed. So since this L is changing, that is why this quantity is also changing, right? Suppose you start from sun, a solar neutrino just started its journey. Then on the way, what is changing? The L is changing. And that is why things are oscillating, because it is a L by E phenomena. The energy of the neutrino is fixed. This theta, this delta m square, they are fixed. But since the distance is changing, or in high energy limit, your time, L is equal to T basically. So when time is changing, okay, so you can see that this probability is also changing. So frequency is not changing. Frequency is fixed, but we don't know what is the frequency. You need to do the experiment. You need to measure the left-hand side quantity, and then you need to fit the data to infer what is the frequency. This is the goal of the neutrino oscillation experiment.
The next question is there any relation between dark matter and neutrinos?
Good question. Very intriguing question. People think that, like, what is dark matter? You can't see them, right? That's why it is dark. Like, we don't know their properties, but we know that in the energy budget of our universe, or around 25% is dark matter. Now, there are theories. People think that these neutrinos can also be a part of this dark matter. But one thing I can tell you, that neutrinos cannot be only the source, only dark matter, okay? Because the amount of neutrinos are so small to fulfill that energy budget. So this is an open question that whether these neutrinos are basically can be a dark matter. But remember, when I talk about active neutrinos, in my first slide, I told there are 3 active neutrinos. That means they interact with W and Z boson. So then they can't be dark matter because you have detected them. But there are something called sterile neutrinos. Why they are sterile? They are very heavy and they don't take part in weak interaction. So there are concepts, there are models where these sterile neutrinos can make some part of the dark matter, but not the whole dark matter. Okay. So good question. I would suggest that you think about this.
So the next question is, if the neutrinos do have mass, then is it possible that they interact with Higgs field?
Good question. So think of, I give you an example of electron and electron type neutrino, okay? If you know that Higgs is responsible to give mass to all the other particles, but not neutrinos, because when Higgs give mass to electron, it needs to talk to the both left-handed electron and right-handed electron. But since in standard model of particle physics, there is no right-handed neutrino, only left-handed neutrino. So the usual Higgs mechanism is not responsible or can't give mass to those neutrinos. You need something special. And there are many theories. One of the popular theories is seesaw mechanism. I don't have time to explain, but if I go to Bhubaneswar and I go to your place or you come to IOP, I can explain to you that you need something different than Higgs mechanism to give masses to neutrinos. So neutrinos in that standard model of particle physics is very special. They say that we are very tiny and look, you can't give masses to us through Higgs mechanism. Okay, you need other mechanism.
Thank you, sir, for attending a question with lot of efforts and clarity. Do you have any further questions?
I don't know, my voice is breaking, so I don't know whether I could answer all the questions, but whatever I could listen or I could speak because my voice is getting broken. So, but if they have any question,
No, sir, your voice
have
is
question,
very clear to us.
It is very
okay,
clear.
that's good.
And your
Because I have a bad cough and cold, so that's good. But if they have any question and they can't ask, because sometimes I have seen in Bhubaneswar, students are very meritorious, but they feel, they think twice before asking questions.
Yes, sir.
So,
I want to invite you. I want to invite you to.
They can email me.
Talk through physical mode.
So they can post questions in our Facebook and Twitter. We are very active, and they can write to me. I will share my slides. I have my email address. So, they should not suppress their curiosities, because that is the first birth of science. So they should ask question. And believe me, when you ask question, I learn every time. Okay. That keeps us going. So please ask question. You can write to us. You go to IOP. I have my group. You ask the questions to those young students and postdocs that we have, and they should be able to answer your question. So go to IOP. That is why Institute of Physics exists. We are there to fulfill your appetite, scientific appetite. Okay. So go to our institute, talk to the faculties there, and talk to the students, and they should be able to answer also your questions.
Yes, sir.
Yes, sir. So this was the session, end of this question answer session. On behalf of Department of Physics, I would like to thank Professor Agrawala for sharing his expertise with us. Thank you, sir.
Thank you, Sandeep
Thanks
sir,
a lot.
for joining us. And I want to
Yeah.
invite you for a physical mode of presentation in our institute. When you will be coming to Bhubaneswar.
Sure.
Yes.
Now I'm in Madison,
Yes.
but if in future there will be opportunity, I would love to go there. I invite you guys to come to IOP because we exist because of you guys, and you are doing a fabulous job in a big university, training so many good students. And IOP, the Bhubaneswar is a pool of good students, and our OUTR is very important, playing a good role. So nourish those students.
Yes, sir.
And if they can ask questions, we are very happy. They should write to us. And if you want, I can share my slides with you and you can share with them.
Yes, sir.
Yeah. Okay. Thank you.
Thank you. Thank you, sir.
Thank you, sir.
So our next talk is by Professor Bhubaneswar Rao sir from North Texas, USA. He is my childhood friend, schoolmate and college mate. I welcome Bibhu sir to our FDP webinar, and I request Prachi madam to introduce sir to audience. Prachi. Welcome Bibhu sir.
Yes, welcome.
After such a wonderful educative session, it is a great privilege to have our next resource person, Professor Bhubaneswar Rao from University of North Texas. He has more than 27 years of experience in research involving ion beams. His research interest involves nanoscience and technology. He is one of the world's greatest experts in the development of a new generation ion microprobe using ion accelerators. He has worked in several laboratories in India, Australia, and USA. To his credit, he has published more than 100 peer-reviewed publications, supervised 7 PhD students' theses, chaired international conferences and topical sessions. In the past several years, he has been awarded with several grants from funding agencies like National Science Foundation, Division of Research and Innovation, University of North Texas, DOD-ARL, Indo-US Science and Technology Forum, National Electrostatic Corporations, etc. He has also been conferred with Ralph E. Power Junior Faculty Enhancement Award from Oak Ridge Associated Universities, USA in the year 2008. So let's welcome Professor Bhubaneswar Rao to deliver his talk. Sir, please.
Okay, thank you very much for the kind introduction, as well as let me thank Dr. Babita Ojha. We both grew up in the same building and the same batchmate, so she knows much more about me. So, and also I have a special connection with OUAT because I did my BSc from College of Basic Science. So when it was part of the CET, and I have played both cricket, football, and hockey for OUAT. So I know pretty well. And since 2007, I'm a faculty at University of North Texas. So I'd like to share my screen. Let's say your present, your entire screen. Just give me a second.
Yes, sir.
Yes. Okay. Hope you can see my screen, right?
Yes, sir.
Okay, so let me do the slides. Okay, you should be able to see this one.
Yes, sir.
Okay, perfect. So as the theme of the talk is, your symposium is quantum transition from ions to cosmos. So what I thought is like, I'll give a little bit of description about what is ion, and then how we are using ion beam to investigate material which are there in outer space, as well as regular material here in our general life. So first of all, ion beam means like typically atom is a neutron. So inside you will have nucleus, and surrounding that we have electron in various orbitals. So if you take one electron out, it's become like charge. Either you add one, it become negative. If you take one, it is positive. So that we call ion beam. So these ion beams, if they undergo electric field, they can be accelerated. So typically, based on the amount of the electric field, they can gain the kinetic energy, and based on that energy, they can be inside the materials or can be deposited in the surface. So we use light ions like proton and helium to go deeper into material for ion beam analysis. And heavy ions, typically we deposit them in the surfaces to make various alloys, which is normally not possible using the conventional growth method, where you deposit one layer, then go another one. This is a top-down model. So ion beam has been used mostly for our investigation for energy-related studies, environment, as well as health. So typically we use this one for material modification and analysis using ion accelerators. Of course, before doing the experiment, we have to do a lot of computational work. And then the typical material or subject area we investigate is astrobiology or astrochemistry, then nuclear materials, and of late, space photovoltaic. So in fact, every alternate year, we organize a conference called Conference of Application of Accelerator in Research and Industry. This has been going on for last 50 years. Every alternate years, we run that here in North Texas. So in fact, I first came to US in 1994 to attend one of these conferences. And a related conference in the spring of 2023, I'm organizing, this is called Material Research Society Spring Meeting. And this particular symposium is more on radiation hardness of next generation semiconductor electronics in space. So having said that, typically, how did we early investigation happen for to know about the ion beams? It was Rutherford and his students. What they found that they did a simple experiment where you take a alpha particle source. Alpha particle means it's that two electrons have been stripped out of helium beam, and they were slightly heavier. And then when they collided with gold particle, they had a scintillating pad outside. And this is a very, very small activity. And they found that every 1 in 10,000, the beam reflects back, rest of it passes through. And based on that, they concluded that maybe the central part is the heavy one. At that time, the atomic model they were just developing, and then and the rest others are hollow, and the size of the central part is maybe about 10 to the power minus fourth of the whole atom. Later on, of course, we did some other experiment. We found that atom's dimension is about less than an angstrom. And then the nucleus, which contains the heavy part, proton and neutron, is about a few femtometers. Later on, they did some more experiments, bombarding alpha particle to metals, and then looking into through microscope when it falls on it, some of the scintillators. and found out the more structural part of the atom. And then more people developed a bigger accelerator, when in fact the very first accelerator was developed at Cavendish Laboratory by Rutherford and two of his students, Cockcroft and Walton. What they did is like they added few transformers. Each one is a 200 kilovolt, made it of 800 kilovolt. Let this transformer go through this RC circuit to produce a DC voltage. Using that, what they did is like they transported proton beam and bombarded into lithium target. If you look at the number of protons and the electrons, the product was 1 plus 3 equal to 2 helium, and then of course 4 proton and neutron. So very fast experiment they did is like they artificially produced 2 more ion molecules, which were atoms, which was just artificially bombarded one. That time it was pretty big news, and some people are a bit skeptical because are they going to create a monster? Like the same sentiment people now have for the Higgs boson. And so this was the very first experiment or development of accelerator. In fact, Cockcroft developed this one in 1932 and 1951, they all got Nobel Prize. Cockcroft spent after 20 years here in North Texas, the same lab where I'm working now. He spent a year as sabbatical and developed a similar equipment. And that up 72 now, it's like after 50 years, that machine is still running. In fact, last year, one student got PhD out of that machine. It was pretty robust one. But modern day, we have much higher machine. So why ion beam? The reason is ion beam is slightly heavier than electron. So when the electron beam interact the material, since they're lighter, they get scattered. Even if you can use the de Broglie's wavelength, which can produce smaller sizes for electron beam, but they're light, they get scattered. But for the ion beam, they can go into the material much deeper without losing the resolution. So this could be used to investigate the materials, image the material which are buried in the sample. You don't have to thin it or nothing. So these are some of the early experiments. This was done in Oxford. One of my collaborators, Mark Breeze, who is currently at National University of Singapore, he took extremely small amount of proton beam. And in fact, it goes along this one, most of the damage. When it goes here, usually they do not interact with the nucleus. Only once they slow down, they interact with the nucleus. So they basically, along the path, they don't damage anything, only the damage end of the range. In fact, this is one of the principles. People use this one for proton beam therapy to kill some of the cancer cells in the body without any surgery. Because initially in the surface, this is just a trajectory of ion beam goes here and how it loses energy. In the surface, very less amount of energy lost, but it can go and deposit much inside. So because of this unique properties, ion beam has been used in many materials for investigation. So currently, new generation quantum computers have been fabricated using ion implantation. In fact, when I was doing my postdoc in University of Melbourne in Australia, we had an initiative to implant 20 keV phosphorus 31 into a ultra pure silicon. Silicon's mass number is 28. So when you put P31, so one extra electron is always available. So using electrical circuitry, one can control the spin of that electron. So it was proposed to fabricate a quantum computers whose spin can be manipulated. So we call it like qubits. So original idea was deposit them with a 20 keV with a separation of 20 nanometer. That's extremely small, and biggest challenge was we cannot produce or deposit more than one ion. Either you put 0 or not 1. So if you put more, then it's too much. But what we did is like we took a atomic force microscope's head, drill a tiny hole. Through that, we irradiated this one. So 2002, we demonstrated the first case. We just deposit this one, but the computer was not made. Then after, it took almost 20 years, around 2018, the first set of commercial qubit or quantum computer was available to run. So currently there is a company out of Sydney, and they call it Quantum Computer Private. People can ask for beam time and run the program. The speed is several hundreds of gigahertz. So, and these are all fabricated from the top-down approach, where you implant phosphorus 31 to silicon 28. Then there will be top a oxide layer and then some metal contacts. And by applying field, these the electric and magnetic field, you can manipulate the spin. So these are the applications. Either you can go deep for proton beam therapy, or in the surface, it can be used for electronics. So my current lab has 2 ion accelerators. I did my PhD in Institute of Physics from 1994 to 2000. We had a similar accelerator like this blue one. They both were fabricated exactly same year and installed around 1990. So here I have 2. One is a single-ended, means the ion source is inside, it produces ions, and we use that as an ion microprobe. And the standard one has a ion source which is outside. We can extract this beam and irradiate material at the low energy, or we accelerate it and irradiate some of the high energy. So this has been used mostly to synthesize materials for astrophysical importances. So this lab has a long history, started in around 1970. And I'm, in fact, 2007, I replaced one of the oldest professors. And now, we have a group of, currently, these are the faculty and students. These are the 2 senior professors, and then myself, and we have some students. In fact, there is one girl whom I hired from Utkal University last August. She joined, and few other Indian students, and the rest of us are local Texan students. So our current studies are mostly to fabricate ion beam microscope. It's similar to electron beam microscope, but we can use this beam to investigate the material, do the elemental imaging. We do analysis part, mostly biomedical samples, like different parts of the brains of the rat. Typically, these rats are fed with some pharmaceutical drug, and mostly to deal with, idea here is like the rats behave similar to mammals. So if they have been fed with certain drug related to diabetic, Alzheimer's, and we need to find out where exactly in the brain these drugs are accumulating. Then a lot of investigations are now going on post-COVID into medicinal plants. Most famously Indian herbal plants like neem, tulsi, even our what we call in Oriya, hibiscus or mandar, those kind of plants. And then we modify some of those materials, which are for solar cell material, typically mimic the environment in the space. And there are new kind of material which are coming up called alloys, which are called high entropy alloy. They have a capability of storing a lot of energies. So the growth in this field will be more into battery and capacitance, small size capacitances. And then we are producing defects in semiconductors. These are mostly application for optical, magnetical, and electronic applications. So some of the students here, we had graduated, and now these are the current students. I have about 5 students. So now coming back to how the ion beam interacts with the material. Typically, in the central region, we have the nucleons, protons and neutrons. Surrounding them, we have electrons in various orbitals, K, L, M, you can think about. So when a light ion comes in, it can either hit the nucleus or the electrons. So if its energy is higher, it can hit the nucleus. And typically, not too high, then it will backscatter like a billiard ball. So we call it elastic backscatter, Rutherford backscattering. So this technique, what it does, like this tells us the composition of various layers in the material as a function of depth. So these are without doing any chemical or etching method, one can do it non-destructively, and the sample will be available for any other application. Other technique is, if any of these electrons get energy from the incident ion, those electrons will either escape out of the material, that we call secondary electrons, or they can go to the higher orbital. But again, that's a pretty temporary stage. They will come back to their original stage for the stability. So this energy difference between the higher orbital to the lower orbital, we call it characteristics X-range. So those will be similar shape and based on the element it has. So this technique we call particle-induced X-ray emission. So based on the amount of the material it is there, the peak height will be changing. So we can mathematically analyze this area under this one and attribute to that to amount of material they have or the concentration mapping. So those one, like we can go parts per million very easily. And in fact, parts per billion is possible under certain circumstances. So what are the material we're looking for? All these plants and human tissue, or even air samples. I have got a lot of air samples from Unit 1 market just to find out what kind of pollutant they are. So mostly these are sand-based. We get silicon and oxygen, iron a little bit. But I have colleagues who are from Middle Eastern, like Syria, Iraq. Those have a lot of heavy metals, and those are not good for human consumption because they go through our respiratory tract and then start cancer in the lung cancer. And there are other techniques we'll discuss as we go down. So we can use this one, for this interaction for analytical characterization part. So even with a very low mass like proton beam, typically based on the energy of the beam, these are like 1 MeV is about here in the keV. Low energy are typically used for testing the space devices. Somewhere between 1 to 2 MeV used for ion beam analysis, or create the damage in the nuclear materials, just imitate as if they are inside a reactor. And hundreds of MeV we need for going through about 10 to 20 centimeter into human body. They're used as a proton beam therapy. In fact, in Chennai, AIMS, not AIMS, this is the other hospital next to the Institute of Physics. They have a first proton beam therapy in Chennai. Apollo AIMS has the first proton beam therapy in India. So, well, when the light beam goes into the material, the beam can go much deeper. This is like in the depth scale about 20 micrometers. 1 MeV hydrogen can go into silicon about 18 to 19 micrometers. So typical width of our hair is about 100 micron. So this can go up to 1/5 of that distance. But if we use the heavier mass like carbon, silicon, they usually deposit in the surfaces. So normally we use the light element to go deeper to analyze the material, and heavier ions to make nanostructures in the surface. So what happens is the technique where we deposit the ion beam into the material, we call it ion implantation. When you deposit little bit at the low energy, they deposit all in the surface. But since they're massive, they actually sputters out some of the layers. But once we put a lot of them, the tiny amount from the start from the tiny dot, and they can collage together, make particles which is about 2 to 3 nanometers, and then they go bigger, and after certain treatment, they can be layer by layer. So typically the flash drive which you are using, those are mostly cobalt disilicide layers. Cobalt is implanted into silicon. They make 1 cobalt to silicon. So those layers, so those are more like a magnetic storage devices. This is like same as your record players where you magnetize those tapes. So I'm sure probably none of you have ever used those one, but flash drives are typically made out of implanting magnetic materials into the semiconductor silicon. So in fact, this is a technique where in a resist material called SU8, either SU8 or PMMA, I use one beam which has a larger energy. Wherever the beam goes, it exposes and make it harder. And then I come back with a smaller energy to make in the top. You can make a cantilever here. These are typically used for tiny MEMS devices or reaction chamber for chemical reactions. And sometimes we can develop another layer on the top, multi-dimensional microstructures one can fabricate. So since in the beginning I talk about high energy focus beam, so I'll show you an example of that. Typically they're developed in a specific beam line, and they're same as our camera, where you have an objective lens and there is a eyepiece, and together they focus the beam into certain place in the target chamber. So only difference here is instead of optical lens, there's a made out of electromagnets. Like you pass the current through this one, those magnets can focus the beam. And using the matrix method, we can do the ion optics calculation by placing these magnets at various locations and increase the magnification power of this one. In this case, demagnification. So these are some of the simulations. You think about a beam which goes here and using the magnetic field. So you focus it. Sometimes we work with 2 magnets or 3, or go with the 4 magnets. So the 4 magnets are easier, or we call quadruple one. However, they're difficult to align, but after many weeks of work, we can focus them. And in fact, this is one of the beamline where I have developed, and these are some of my students there. They usually work in this beamline here. And we usually, for measuring their ultimate scan width, we scan them on a transmission electron microscope grid. Typically, size of this 2000 Mets means there are 2000 holes in an inch. So typically, the distance from one central portion to another is about 12.5 micron, and the bars are about 5 micron. So the beam size is about 0.5 micron. So these are like using doublet, triplet, and quadruplet mode. I can focus them to much better sizes. So let's look into some of the applications. So one of the applications what we were looking into are trace elements in the breast cancer tissue samples. Typically, in the breast tissue sample, there are areas where calcium, milk is stored, and that's basically calcium. But once person gets older, there is a loss of calcium, then foreign material arrives there and they start typically copper 2 plus, zinc or manganese. They start the king size, means uncontrolled growth. So we were able to image this tiny storage here with various resolution, and then we go in and try to find out how much metals are there. These are typically called early detection, and they take about 20 to 30 years to become a full-fledged tumor. But if we find that, if this test find from the, you take a needle biopsy, means like the size of the needle is about 0.25 millimeters. Typically, let's say somebody's mom or grandmother had breast cancer, then people usually, they're careful and they like to do the pre-screening. Age from 18 to 30 years, they take a tiny tissue samples using a needle biopsy, and then they put them in a slide, and we used to scan them. Again, we don't do we do just the research, but there are other labs who do this one like a regular diagnostic part. So the size of this particular sample is from here to here is about 80 micrometers, like 0.08 millimeters. And we are able to find some of the trace elements here, and then later on, the patient goes for the therapeutical route, how to delay it. Then the other one is like of late, I had a student, her name, she's from Chandigarh, Punjab. So she picked up, Punjab University has a pretty strong biophysics group. So what we did is like we got a few neem leaves, then tulsi, and then hibiscus, and which has like a green, and if it is older, then yellow. And these the square pattern which you see, these are the areas we scan it, and these are the corresponding image here. The reason we did this one, these are like imitating the tissue samples, so you don't have to take any clearances keep the bio lab like a bio, you don't have to go through that large protocols, because after COVID epidemic, all the labs are very, very careful, particularly if they're not biology lab, they have to be careful how to deal with these biosamples. But with the leaf, you can use as much as possible. So these are the areas, like it shows how the stem part is here. Typically, as I showed you, like our bones are made out of calcium, but this particular leaf was old, so the calcium, only tiny blocks are there. They basically breaks down, but made out of potassium. And similarly, for hibiscus, the one with the green has less amount of chlorine. So chlorine, what happened that, when we have the photosynthesis, that time the chlorine is accumulated. So once the leaf become older, they actually accumulate more amount of chlorine. And there are some light ions are there, like phosphorus, sulfur, and sodium. But this is the heavy one, which are there. And what we did is like, we using our technique, again, as I mentioned, like the beam goes in here, interacts with the electron, produces this X-ray, the characteristic X-ray. So these are typical spectra. Each of these peaks can be assigned to specific elements. And we use appropriate background subtraction. Sometimes if a lot of counts are here, what we call pile up, like these two peaks can add up and produce a signal. So all those things after subtracting, we can find out the area under each peak, and they are directly proportional to the concentration of the materials. These are the various elements as a function of atomic number. And we can come down to concentration of nanogram per microgram or milligram. If you take a tiny area, and we can go 10 to the power minus sixth of this. And some of the previous experiments, they were able to measure only top from here. But with a very sensitive technique like us, we can go down much down here. The whole idea was, what are the is the concentration of some trace element, is that important for therapeutic implication of these leaves or not? So that is what is our investigation. So these are just like a three element projection distribution. If you could see this pink in potassium, those are like a tiny pixelized areas are here. And so they vary from different type of leaf. So in fact, what we found that Tulsi leaf had a thick portion and very thin portion also. And we're still investigating a technique or simulation code. This is called transportation of ion in material. This is a binary collision approximation, like it does every collision series-wise, using a random number generator we call Monte Carlo transportation. So what it does is like, it can tell that how much depth the ion beam can go. But as we normally, you expect, let's say 50 keV iron into silicon. They're typically used for making various channels in optical fibers for telecommunications. But once we increase the number of ions, then they start sputtering and then they get saturated at a certain depth. So we know that how much concentration ratio we can produce using this certain amount of energy and the fluences. So another technique which we did is like, while we were implanting, we actually had a magnet surrounding that here. So what this magnet does is like, when you irradiate them under a magnetic field, it can produce or align those ferroelectric magnetic domain along these north to south directions. So this was helpful for us to create a specific alloy of Fe3 silicon, and we can use cobalt silicon or make a ratio of iron cobalt silicon. These are called Heisler alloys. So these are some of the TM images which shows all these clusters. So, and then we can investigate them, find out what are those elements are here, alloys here. Depth-wise is fine if it is a flat sample, but if it is like a nano samples, like nanoware, then the beam actually can come from the side and some of them can lose it. So some of the simulation need to be done in a 3-dimensional one. So for that, what we do is like, inside part we simulate as if a flat layer, but then we make it in the side here. So typically, let's say this is a nanoware and you are irradiating it. So you have to find out the same distance from this edge. And you can create a nano tube of this material if the nanoware is rotating. So in fact, what we did is like, we put them on a target holder and the holder is rotating constantly. So idea was either we sputter it and make a alloy of the nanoware, or with a lower energy, inside part will be still the original material and outside we can make a nano tube. So these were the nanowares initially. In fact, I imaged them in nicer in Bhubaneswar. And after the irradiation, they can thin down with an alloy like this one here. So these are cobalt, iron, silicon, typically used for ternary alloy system. They are called like memory safe devices. Based on the amount of the magnetization, the shape can change. So these can be used for switching devices in extreme conditions, like inside the reactors, satellites, so those kind of environment. So now coming back, so next was based on our experience that irradiating multiple elements at certain energy, we can actually, through the simulation, we can create a specific alloys deep down here. So how is that related with the astrophysics? Typically, there are several different kind of stars when they are developed out of the galaxies. So based on their luminosity and the temperature, they follow somewhere in the middle that we call main sequence. So the main sequence then it's become a red giant star. Then it comes down to a smaller one, and then come back to further smaller one. And based on the temperature, cooling temperature. So from here, they can white dwarf is a very small. When the temperature comes down, it basically hydrogen, helium is bonding into hydrogen outer shell. So the stars are here, but in the planets, they are further away from the stars. So once they cool it, the planets develop. So typically, let's say this is one star here, and about 5 times the radius of that to 100 times the radial distance. This is where the element which are emitted out here, the hydrogen, they start cooling down and then make the molecule. And the smallest molecule which we called has a life is called amino acids. Those are actually formed somewhere in this distance here. And these are, we are mostly looking into the formation of organic molecules. So based on the pressure and all, you can have the heavy elements. But then once they cool it out, then outside is really cold and they get frozen inside. So in fact, the new missions of NASA tell that our universe has so many places, they have huge amount of water is there. Now they want to send the satellite, do the experiment to find out, do they have tiny molecule where their life exists? They're looking into amino acids. They will do a few experiments, mostly infrared experiments where to find out the absorption. However, before going there, we need to prepare these compounds in the laboratory and look into those tiny desorption experiment and see what kind of signal is coming out. So I have a collaboration with Jet Propulsion Lab of NASA in California. What their idea is, we can create some of these are called dust outside the space. In fact, they are not vacuum, but there are so many dust. These are the parts of the, like you have the planet breaks down, you have a meteorite, then meteorite breaks down. These are all bombarded with continuously with cosmic radiations, and then we get tiny, tiny dust. And some of them are called forsyte, firelight. These are like olivine. These are basically a mixture of silicon oxide, magnesium, iron, H2O. When I told you, like I had analyzed some of the dust from Unit 1 market in Bhubaneswar, these are the real earth-based dust, mostly made out of silicon dioxide, iron, and magnesium 1. Inside is magnesium 2, silicon 2. And so they can be available in various phases. So we use the ion beam technique to produce them or synthesize them. So our aim is to use the low energy iron and magnesium into silicon, and then use the high energy beam to give the high energy induce annealing in the track. So before doing the experiment, we'll implant oxygen, magnesium, iron into various concentrations. Our idea is to have a total amount, like this is the concentration ratios, and the maximum in the matrix of silicon, it is here, and then various layers. If you see here, the orange is magnesium, iron is here. This is one iron and one magnesium. And then we go into 3 times more oxygen, and then 5 times more silicon. So idea is up to certain depth, about 100 nanometer, we can produce these layers. So after the irradiation, we did the thermal treatment, and we were able to successfully produce tiny nanoparticles of what we call magnesium-oxide. These are material made out of magnesium silicon oxygen or iron oxygen or a combination of this one. So and when the electron beam comes back, so it gets scattered, like many of you might have studied about superposition of light for interferences. Typically, interference pattern is, in the book, they'll be showing a straight line and you have a central maxima, next maxima. But when you do the electron scattering, you have scattering on all 360 degrees. So instead of a straight line pixel, you get from a radial distance one circle that will be correspond to the first brightness, second brightness. So for different atomic combination or lattice combination, we can produce various rings, and that ring can tell us what is their separation between those lattices, which act as a slits. So the next item I want to talk about is how to power the space satellites. Currently, most of the solar panels which we use in our houses are silicon-based. So this is a map about the efficiency versus their development over the year. This particular roadmap is developed by National Renewable Energy Laboratory in Colorado. So mostly the silicons starts from 1975. Their efficiencies right now stalled around 20%. But recently, since 2012, there is a new kind of material has come up, which is called perovskites. It's a mineral initially discovered by a Russian scientist, and which has been making steady progress. A perovskite and silicon combination can go up to 48% or even higher. So why we are not using it at our home? Because it has certain challenges. The biggest challenge here is typically they have issues with the thermal stability. Like silicon can stay in the cold or hot or rain, but these have some sort of moisture problem. Typical structure is they are made out of simple cubic structures. At a molecule which are methylium or formaldehyde or cesium, like one electron outside. It's called one extra, you take it out, it's anion. And in the body's center in the middle, there is either a lead or tin. And in the face, there are 4 others, like 6 faces are there. It is usually typically made out of a halide, either iodine or bromine or chlorine. So the compound typically ABX3. This was accidentally discovered by a Russian scientist and called peroxides. They look like any other mineral. So advantage of this one are they can be thinned. They are extremely flexible, lightweight, extremely high power conversion, go up to right now 28%, but in combination with silicon, it can go up to 44%. And they are solution based, like you can use a dropper and spin coat them. And usually the material is low cost, but the protection layer is what need to be developed. So these are the new generation solar materials. So for long range mission, typically we need some high power solar materials. So domestic terrestrial application, this can wait for a few more years to develop the protection layer. But currently there is a huge need for extra powering satellites and devices for the long durations. So, last week you might have seen they were doing the spacewalk to replace the solar panels nearer to this space station. In fact, currently the space station is such that half of them are owned by US and its allies, and another half is by Russians. They have been threatening since last few years that they want to take this one along with them, or they want to rent us. So we need to develop this one pretty fast so that replace them sooner. In fact, last August, I gave a talk at one of the NASA's lab in Cleveland. They were mostly dealing with satellites which will land in a moon. In fact, the first one, Artemis 1, just went and did orbit around the moon and to take some images of the exact location where they're going to land. Artemis 2 is expected to be landing in 2026 with an astronaut of color, means like they're not necessarily completely white astronauts, and also a female astronaut. And they are planning to locate a site, and this will be a crater because they are easy to drill through and find out if they have water there for long-term colonization. But the top of the crater, they want to install these high efficiency solar panels, and then they will charge a laser light, and the laser light will transmit the energy from the top of the crater to the base station. So by 2030, they want to have a settlement in moon. And once we have that experience, by 2040, there will be a manned mission for settlement in Mars. So that is why there is a huge thrust to develop high efficiency solar panels in the for space applications. So our work is, once you go to the space, there is no atmosphere. So the cells are constantly bombarded with radiations. So we want to develop some cell which can withstand this radiation at least for 40 to 50 years. Otherwise, we'll have a lot of debris, and transporting materials there is not easy. And other difficulty is, when the moon is between Earth and Sun, the temperature goes much, much higher, about 110 degrees. And when Earth is in between moon and Sun, the temperature of the moon goes to minus 30 degrees. So this cell can work in a wide temperature range. So the thermal stability is important. Then the other one is, most of our launch stations are close to the sea. Sea means we have salt water. So they should withstand attack from chlorine and sodium so that they don't get corrosion. They should be corrosion protected one. So they have to withstand chemical, thermal, as well as radiations, and can able to work high temperature. But the other problem, like there are not just looking into Mars, Saturn, Jupiter, age of the almost go to the age of the solar system. As the further you go, the problem is the amount of sunlight decreases. So they have to be efficient with the low temperature and low light. So we cannot just expect the amount of the sun we have and test it and tell, okay, it is 20% efficient. But by the time it has reached Jupiter, the efficiency is 0.2%. So they have to be enough to power it. Of course, we can put the nuclear one, but then there are other issues to deal with that. So another one, which is getting very interesting. Elon Musk has his company. It's called Starlink. They have got approval to send communication satellites, which are purely for providing internet. Right now, in fact, just few minutes ago, before the talk, I took the images from their control one. These tiny dots are, white dots are the number of low Earth orbit satellites in the current in the space. And these orange dots are the Earth-based stations. So they're typical, it's like a GPS. Use anywhere you go, you can catch the signal from here. You don't need any tower or no cable. So these are internet from space. In fact, currently there is one satellite down here. They typically move around here. But Reliance is tying up them, and they are planning to send about at least 2,000 satellites, which will be on top of the, always will be top of Indian subcontinent. So that like your cable TV, most of the internet will come from them. So there is a huge market to produce solar panel for the space application. So this is a curve. Data was extracted from NASA's the website. Typically, let's say this black one is called low Earth orbit, about 420 kilometers from Earth's surface. That is where International Space Station is there. And these are the number of proton beams with different energies incident per year, like about 10 to the power 10 particle of about 10 keV, or 100 keV here, 1 MeV here, and higher energy, that decreases down. So we need to test our devices with these kind of energies. So typically, the accelerator which I have, I can go up to 10 keV, and we test them up to all the up to 10 to the power 14 ions per centimeter square. So that will give them about, let's say, 10 to 10,000 years of, as if these are exposed to 1,000 years. And we look into the efficiency of those cells. So these are some of the perovskite solar cells. So this is a cross-sectional electron microscope. It tells, like, this is the top gold contact. There is a layer which is just transport the electrons. And this cesium, lead, iodine, and bromine, this is the perovskite layer here. Similarly here. So these are like cesium, lead, iodine, bromine solar cells. These are like a triple cation with more like cesium, formaldium, and methylium. All are here. So we usually mount them in our laboratory to test the efficiency. Then using the accelerator, I can irradiate each of the cell and see what is their efficiency. In fact, similar cells are there in the Mars rover, and they have been constantly giving us the data about the efficiency of that. So with the ion beam, we can tune the energy to target which layer we can deposit the energy so that we can accelerate the testing. So when the ion beam goes in, either it interacts with the electron or the nucleus. So when it interacts with the nucleus, that's where they make the damage. Electrons, they get excited and come down, they just increase the temperature. What we found out, if we carefully tune our energy, those electrons actually can ionize the material, means like create a plasma-like situation and anneal the material. So if there is some damage here, those could be annealed out. So in fact, in one of the American Chemical Society energy letter, we showed that if there is some damage and if we irradiate them with a higher energy, this could be healed back and it can regain its efficiency. In fact, these are with different energies. We are just trying to see which energy would be sufficient. And these are some of the photovoltaic measurement, like we measure their maximum power which can be achieved. So what had happened, it so happened that after irradiation, actually the power went more than 100% at about 300 kilo electrovolt with a fluence of 10 to the power 11. So when I talk about 10 to the 11 means they are up here. So this is like 10 years of life in lower Earth orbit. If it goes to Jupiter, that's almost, we need to go higher up here. So then another thing which we notice is like we can irradiate with very low energy to make damage, or in a very high energy where you deposit the electrons and ionize it. So each of them best produces different kind of defect. And also what we found that if we store them in a environment where there is darkness, after a few days, they actually regain back their efficiency. So this is important because when the moon is revolving around Earth, so when it is between Earth and sun, it's actually daytime there. But when it is back to the no moon day, when it is behind the Earth, that is the darker time. So if we give them like every 15 days, it goes through this cycle. So there is a chance that some of the cell can regain its efficiency when it is in the dark one, or heal back. So that's one of the greatest benefit of utilizing these cells. And in fact, for the first time, we discovered this one. Some people, they had a hint, but nobody did the systematic measurement. So that's been accepted in a multidisciplinary journal called Joule. So, and these are some of the simulations with the low energy. This like the device looks like there. Top, you have a metal contact, then another through which you take the contact out. It produces electron hole, and the sunlight falls on it. And then when the electron pass through here, that's where you get the current and your solar panel works. So we decided that if we put a tiny layers of cover glass, they can stop most of the radiation in the outer space, but allow the glass, because glass is transparent, allow the light to go through the glass, but the ions can be stopped here. So some of the work initially we told that we don't need to have very high energy, but this protection layer can cover silicon oxide-based protection layer can cover these cells. So the paper came out in June just a few months ago. And in fact, it was the cover page of the journal. Then also we showed that using this perovskite-based observers, it can complement or even do better than the other traditional solar cells based on silicon or indium gallium phosphide. So because industry, these are the pretty solid materials, they're very the crystalline materials, but perovskite are more organic, flexible. It has the advantage of making flexible electronics, but people are skeptical of using that in the harsher environment. But we showed that they can be this observer, they can produce the same efficiency as the silicon or better. Then what is our future plan? So currently we are investigating, like irradiating with them in many different energies to create the same type of data as the International Space Station generated for protons. And these curves are for 3-5 semiconductor. They're pretty good up to 10 to 13 particles per centimeter square. But we have shown that it can go 2 orders higher, like 100 times better. So idea is like, let's say we send a satellite to outer space, like edge of the solar system. It will take probably 20 years. So the cells can still be efficient and power it up. And we develop a new, it's a typically glass is silicon dioxide, but we develop a new barrier layer, it's a silicon oxide. So when you put that one, typically if you do not have any barrier layer, initially it starts about 18-19%, but then within a year it damages to almost zero. Whereas we showed that we can irradiate them for radiation worth of 10 years, it can go from 18% to about 15%. And these are different NIP device like PIN, P intrinsic and negative type. In that PIN, it's almost retain the whole efficiency. In fact, this is just like a couple of weeks ago, it just accepted in Nature Energy. It's one of the highest impact factor journal in our community. So another thing is when the ion beam goes in, as I told, it can produce electron hole. So the sample could be a detector. So, but the samples for the SCM which you saw that a lot of grains, and the bigger grain sizes, those are like it creates a barrier for inhibiting the transfer of charges. So we don't want to or develop a technique where we can quantize the migration of elements or the edge boundaries. So we use this ion-induced technique where wherever beam goes, it can measure or collect the charges. It's called ion-induced charge collection mapping. And basically close to the electrode, efficiency is higher, it goes further. This is just the charge collection efficiency. So if we make a solar cell which has multi-grain, and this gives us an idea like how closely the electrode has to be. Or you can apply more voltage to attract those electrons. So this is an image in a silicon, traditional silicon, which are made of the polycrystalline one. And the optical image looks like along the edge here, there are areas which are low efficiency one. So our idea now is to test those perovskite to find out what kind of materials are here and what are how could we alleviate the problem due to the accumulation along these grain boundaries. So because there are so many, but as it looks like there are this way layers are pretty big. So if I have a contact here and further another millimeter down here, it's very easy to do the screen printing of the layers. Then it will be efficient one. But before that, somebody need to do this experiment to validate that these grain boundaries are not inhibiting the electron hole pair travel. So that's pretty much all I have. So thank you very much for the opportunity to speak.
Thank you, Professor Raut, for providing such an overview of the importance of ion beams and their interaction with matter depending on their energies, the importance of synthesis of cosmic dust or silicates as an important messenger that carries information about various space phenomena and for space application was indeed thought-provoking. So after this informative session, I'd like to share a few questions from the audience. So Professor, the first question is, how could one decide the ion dose rate for a specific material for any specific application?
Well, typically what we do, like we use a Monte Carlo simulation. You take a target and you define the layers and what is your target layer, and then let's see if I could show this one. So let's say, yeah, can you see my screen? Okay, it's probably going back.
Yes, sir. Now it's visible.
Yeah. So what happened is like we do a simulation along this x-axis, we'll have our layer thicknesses here, and whatever ions we are irradiating it, for certain number of ions, we can simulate and find out how much of them are deposited here. Then, if you have to do multiple ions, on top of that, you do another simulation. It will create a new layer, which I've already deposited down here. So then what you do, like you take the sample and irradiate them with a specific beam. So the sample will be connected to a current meter. So each charge, electron charge is 1.6 times 10 to the power minus 19 coulomb. So we can measure about few nanocoulombs. That means 10 to the power 10 particles. So 10 to the 10 is a huge number of particles. However, as you know, like if you take a 1 molar mass, that's about 10 to the power 23. Typically, a layer of the material in a centimeter has about 10 to the power 22 atoms. So all we do is like we measure the current, or the current will tell us the number of ions are hitting the target or depositing. So whatever concentration we need, we measure it for up to that much of the current. Some of the irradiation can take as little as 1 minute. Some of them can take whole week. So depending on how much concentration we want to deposit.
So the next question is, the biological samples having complex biomolecules, how can one identify each individual element?
Well, nature has done in such a way that you see this X-rays here. Can you see the X-ray images here?
Yes, sir.
So for each element, it produces its characteristics X-rays. And we have efficient detectors. Their efficiency such that we can differentiate each lines here. So then we take, when Ranjan discovered this one, these are called Bremsstrahlung. So when the beam comes here, some of the electrons will come out. Those are the breaking background Bremsstrahlung. But the one which goes to the higher orbital and comes back, that's the characteristics X-ray. So we can tell what are the areas under each peak. And the peak, for example, this peak corresponds to potassium K alpha. This is calcium K alpha. This is manganese. This is iron. So you could see amount of iron is much lower than the calcium. And copper, in fact, is few. So using this area under each curve, we total them to 100%. So the material which is there in abundant, there will be like 10 to the 5 out of a million, which is 10 to the 6, so 10% or something. We can come down to not just the percentage, but like parts per million, that low values.
Okay. The next question is, how the biological samples to be managed in high vacuum chamber for composition analysis using ion beam? Further queries are also regarding beam current and fluence.
Yes. So what happens is, typically what we do is like we freeze dry them. Like you put them in liquid nitrogen, they get frozen, and then we have a slicer. It's like a very fine blade. It can slice about 20 micron thicknesses. For example, the lips, we basically dry them using a UV lamp, and then there is not much water, but they don't, if you quickly dry them, all the elements stay in their locations. Only the hydrogen and oxygen goes out. And they can be vacuum resistant, that's not a problem. and then the ion fluence to analyze it. These all are depend on how much statistics you need. Suppose I need 10 to the 5 counts. So if we put a detector pretty close to the sample, it has a huge solid angle. So typically these ones, with our beam, we can generate this kind of image within 20 minutes. Those are about few nanocoulombs of radiation we need it. It basically, we have some detector which has a large solid angles, and the total scanning area of these samples, like from here to here, the blackened area is about uh, 0.5 millimeters, 0.5 millimeters. So we irradiate them for about 200 to 300 nanocoulombs. Nanocoulomb means like 10 to the power minus 9 coulomb. Each charge is 10 to the power minus 19. So it's about 10 to the power 10 number of particles. And out of that, they can generate almost 10 to the power 5 or 6 counts up here.
Our next question is, what is the interaction cross-section of proton beam in space? How can it be compared to proton beam for accelerator on the Earth?
Okay, so that's a very good question. And in fact, if you look at here, this tells that for in a 1 year time, let's say at the International Space Station, which is about 420 kilometers from the Earth's surface, at 1 MeV energy, they get about 10 to the power 10 particles per centimeter square area. That many number of particles of proton hits. In fact, using our accelerator, we can generate this one, and the equivalent fluence will take less than a second to do this experiment. In fact, I have to diffuse the beam to extend it for, at least I can scan the beam once or twice. So the most of the experiment runs between 10 seconds to a minute, that much of radiation exposure we need. So it's a bit of challenge to reduce the beam.
The last one is biophysics the way forward?
Oh, of course, yes. There are a lot of accelerators. They're dealing biophysics quite regularly. Europe, US, and in fact, we have been, anytime I have gone, I have given talk in Bhubaneswar, and they wanted to develop like a joint biophysics program with the Institute of, I think it's the ICMR is pretty close to the Institute of Physics. Then they have Institute of Life Science. But then a typical regular like Utkal University and other local universities, they have a huge medical engineering departments. So yeah, a lot of biotechnology, like we can make the MEMS devices, which can be used as a sensors. So there is a huge amount of application are there in the biophysics.
Thank you, sir, for your prompt response to all the questions. Do you have any further questions? If there are no more questions, on behalf of Department of Physics, I would like to thank Professor Raut for sharing his expertise with us. Here, we come to an end for the first session of the webinar. After the lunch break, we all will meet again in the next session, that is at 2:30 p.m. See you then. Thank you.
Okay, thank you very much.
Thank you, Bibu.
Yeah.
And I want to invite you to our institute when you will be coming to Bhubaneswar.
Okay, hopefully this year will come. Yeah.
Thank
Okay,
you.
it was nice.
Good afternoon, sir. So I welcome all participants to the afternoon session. Now we have talk by Professor Pratap Kumar Sahu sir from Niger, Bhubaneswar, and sir will be talking on topic lotus leaf effect in ion beam synthesized quantum nanomaterials. So to introduce to the participants about the speakers, I request Prachi madam to give a brief introduction about the speaker.
Thank you, madam. Welcome back to the second session of the ongoing webinar. A good afternoon to all of you. It is our honor to invite Professor Pratap Kumar Sahu from NISER, Bhubaneswar. Professor Sahu is well known to be an active researcher in the field of photonics. He specifically focuses on the fabrication of patterned nanostructures using various lithographic techniques, thin film deposition techniques, and embedded nanostructures using energetic low and swift heavy ion implantation, and studies photonic behaviors, the control, interaction, understanding, and the application of light at the nanoscale, which lead to the design of plasmonic devices with optimized properties. So, I would now like to request Professor Sahu to enlighten us with his experience. Sir, please.
Thank you very much for your introduction. Okay, let me share my screen. Can you see it?
Yes, sir.
Yeah. Okay. It becomes smaller, I think. Yeah.
Yes, sir. You can do it in the full screen mode.
Yeah. Okay. Let me share in the other way. Windows.
Sir, minimize it your browser.
Yeah. Now I'm doing it. Yeah. So now you can see it. Yeah.
Yes, sir.
Yeah. So it is in full screen mode.
No, sir.
Is it not in full screen mode?
No, sir. So please share it to the entire screen.
Entire screen. Then only it will happen. Okay. Yeah. Now it's okay.
Yes, sir.
Yes.
Yes.
Okay. So good afternoon, everybody. Thank you, Dr. Ojha, for giving me an opportunity to talk or share about our current work. Okay. Today I will talk something regarding the lotus leaf effect in artificially synthesized nanostructures. Okay, or quantum structures. Yeah. So if you see this left-hand and right-hand images, one is the natural lotus leaf, where you see the water drop is on the surface of a lotus leaf, where it has it looks like a spherical water ball. Okay. Similarly, we have synthesized something at the nanoscale on the surface of a silicon oxide substrate, where if you see that if you put the water dots, okay, it will look like this, small dots. So we want to mimic that, what kind of structure you can do using ion beam or some other techniques. Okay. Before going to giving the talk, let me introduce that I am from Niger. I hope everybody know it, okay? And one can know details about the Niger going to the website. And in the Department of Physics, we have basically 3 different kind of courses we are running. One is integrated MSc, 10+2, the student give our exam, next exam, then through that they come to the, for doing their integrated MSc, where they do the 5-year MSc program. And then this is after BSc or BTech, we have another program called integrated PhD. If you qualify the JAM or JEST, through that we have our interview. Based on the interview, we take the integrated MSc student and integrated PhD students. They do 2-year MSc here, then continue the PhD. And yeah, those are very good students basically. And then if it is not in BSc, then you can still try in MSc. And after MSc, if you have NET, GATE, CS or JEST, you can come through our PhD programs. So in the department now we have more than 30, near 34 faculties and a lot of scientific officers. And we work on different kind of research like theoretical and experimental high energy physics and condensed matter physics and cosmology. And they are typical distribution of our different 4 groups of the physical science. Okay, we have both experimental physics and theoretical physics. In the experiment, 2 divisions. One is high energy physics and is condensed matter physics. In condensed matter research, we work on ion and photon matter interactions, nanopatterning, photonics and photoelectronics, ultra-cool atoms, nonlinear optics, like a lot of different areas. Okay, and some new areas also introduced now in the subcondensed matter. And in the theory, we have all different kind of condensed matter theory or string theory or particle physics or quantum QCD or astrophysics. They support our condensed matter experimental program. Okay, so my group is involved basically synthesizing different kind of nanomaterials where we look for the interaction of ions, okay? And with these nanomaterials, look for the effect of this electronic or nuclear energy loss in new materials where we synthesize or looking for the bandgap materials or using the bandgap property, produce 1-dimensional, 2-dimensional, or sometimes 3-dimensional based grating, polarizer applications, and large area optical materials for optoelectronics applications. So these are very different structures we produce and we fabricate using thin films, sometimes ion implantation, different kind of lithographic technique. Okay, and then for characterization, we look for FEACM or high-resolution TEM, transmission electron spectroscopy, photoluminescence, jet scan, BOK, and other things. And of course, for the application side, we look for anti-reflecting layers, quantum dot arrays, SPP, or new material synthesis. Okay, with this, let us come to the research programs. And in my group, we do basically a lot of different kind of work. Out of that, I will introduce 2 new work where this talk will not be considered, okay, in this talk. Talk will be in a different area, but apart from that, we have the 2 main areas where we work. We synthesize the zinc oxide nanorods, and in this zinc oxide nanorods, then we look at the twin nanorods. The twin means one side is pure crystalline, another is also crystalline, and these are joined with a amorphous layer of thickness T. Okay, with this small thickness of this amorphous layer, what will happen? We look for the phonon tunneling possibility. That like if I connect to this an electronic circuit as a battery, then electron can flow from this end to that end. Okay, then I see that whether it is a diode or a transistor or such electronic property. Similarly, if I can excite something with excitons, then look that whether the phonons are created. That means phonons are the quantum of thermal energy. So the thermal vibration inside the crystal you see. Okay, like photons is a quantum of the light energy. Okay, then phonons are quantum of the thermal energy. Okay, carrier of the thermal energy. So phonons, if I can transport this phonon from this end to that end, then we need a critical barrier. And this critical barrier, if we can tunnel through, then we call it a phonon tunnel device, like electron tunnel device. Okay, so this is the typical applications of like whether we can transport, like light, we can transport through the fiber optics. Through the fiber optics, if you put a light in one end, the light can go to the other end. Similarly, if we can make such kind of crystalline matrix where phonon can transport from this end to that end, that means thermal energy can be transported through this kind of structure. So these are the one of the future work. People are now looking on, many different papers are coming on these areas, and this is one of our work we look for the tunnel devices. So similarly, if in this case, it can also work as the electron tunnel device of a single nanorods. If you can make such P-type and then N-type, this is P-type, then it's the PNP transistor. Similarly, we can make it a PN only, so PN diodes. So we can create also PN, like that kind of materials like a tandem PN junctions. So those are also useful for optoelectronics or electronics materials. Okay. So what we do, we take crystalline ZNO, zinc oxide nanorods, then implant with a different kind of energy like 50 keV oxygen ions, it will produce a P-type like this here. You see, this is when it is oxygen rich, the N-type pure ZNO is N-type in nature, it converted to P-type. Okay. Then if I do 50 and 150, then 150 the energy is here. Okay. Then it has a density here and it has a density here, in between not much. Okay. So then we can produce 50 and 350. You can have two different layers of active P-type materials, and in between is N-type materials. Okay. So then we can have a PNP transistor. If we can make a source, drain, and a gate through the backgated substrate, then we can have our PNP transistor, and you can look for the transistor characteristic. Okay. And if you put the light on it, then characteristic of the PNP transistor it changes. So that's where light emitting transistor. Okay. So this is one of our recent work we are working on. One student has submitted the thesis on this area, and some other work of phonon related work are going on. Okay. Apart from that, we produce another kind of materials which are called NiBi3. If Ni and Bi, two materials like this, I have a nickel on the substrate of a silicon, then deposit the bismuth. When it will be deposited at the interface, it will make an interfacial layer. That interfacial layer is basically called NiBi3 compound. And this NiBi3 compound is so the coexistence of superconductivity and ferromagnetism. The most interesting fact is when we do such kind of study, then you see in the structure look like very funny. So you see some kind of different kind of structures are coming up. Then why does such structures, surface structures come up? We tried to dig it, and we found that these are coming due to the Turing mechanism. What Turing says that if one activator and an inhibitor presents, that means one a highly diffusing and a slow diffusing materials are there, then it can produce different kind of structures. That's the reason that it is simple kind of like solving the second-order differential equation of Fick's law. Okay, this is the diffusion equation. Del A by del T is equal to F times A by L. F is your basically diffusion coefficient. Okay, dA is your diffusion coefficient. If you solve the second-order differential coefficient, then you find that such kind of structures are produced. Which in nature you can find that cheetah has this surface, giraffe has such kind of structure, jellyfish has such kind of structures, snails has such kind of structures. So all these structures you can see in nature are composed of, and if you solve this mathematically, and you can see that such structures are coming from solving the second-order differential equations. So we tried to push it, and we found that these are coming like this, and this is such kind of second-order differential equations. Then we solved this problem, and we found that what kind of differential coefficient of bismuth and nickel, and from here we say that the difference, the thermal diffusion differential coefficient of nickel in bismuth is low, where bismuth is diffusing to the nickel is extremely high. So one melting point nickel is 1400 degrees centigrade, where the bismuth melting point is at 241 degrees centigrade. So highly 2 or 3 orders of magnitude, one material to another material, the melting point, other the diffusion coefficient is there. That is a very fast diffusion like this. Okay, I told you very fast diffusion, and another is very slow diffusion. So this makes such kind of structures if you solve the equation for this, taking the diffusion coefficient into account and other parameters, then you see that this can be solved. Okay, so now surface structuring, nanostructuring is one of the important parameters where we can mimic our nature. So out of that, lotus leaf is one of the best way where you can see that in the nature. Okay, all the surface of the lotus leaf cannot be wet. Similarly, in the winter nowadays, if you go outside early in the morning, all the grasses you see that it looks like a surface lotus leaf effects, and these are the spherical dew dots as falling on the leaf of the grasses. So this is effect of superhydrophobicity. So this superhydrophobicity is basically called the lotus leaf effect. So we'll go with slower for the student's point of view, that how the student can understand this. Okay, that if I go and see the microscopic effect of this lotus leaf, is then we can see the microscope look like this. Is it able to hear me?
Yes,
Yes,
sir.
sir.
Okay. Yeah. Okay, you can stop me at any time if sometimes you don't understand or you cannot listen me. Okay. So just yeah. So if you see in the micron scale, the surface of a lotus leaf in the microscope look like this. And if you see the structure of the butterfly, then this also look like this. So such kind of nanostructures are there. And in these nanostructures and microstructures, when water drop will fall on it, then what kind of structures? Some nanoscales are on a microscopic scale. Then if you see, depending on the hierarchical structures, then you see the water is all the surface falling on the surface. It is not waiting here or here also not waiting. So the water droplet is why it is not going to the leaf and spreading out. Okay, it is a hydrophobic that will spread out. It is a hydrophilic, okay, phobic, then super hydrophobic, then it will see that it is not spreading out. Okay, hydrophilic, it will spread out. Okay, then these are very good for self-cleaning. If you can clean the surface, whatever dust particle will be there, and you can clean. Because now it cannot wet the surface. Whatever dust is there, it just roll out. Okay, so this is a very good application for the self-cleaning. Now, you see that you see the utensils nowadays. Okay, and if it is a non-stick, it is a sticky one and non-sticky one. Now, the chemistry labs, all these tubes, you will see that this is a hydrophobic surface inside. Then even if the residuals or the chemical you are working, it will not stick to the tube at all. It will just, whatever is there, it will come out. Okay, so then these are very good. Now the surface of mobile phones now, it will, you can, even if you watch, you can see, and they give the water resistance of 50 meters. Even if you go to the 50 meters of water, your watch, nothing will happen. Okay, the surface is completely hydrophobic. Water cannot wet it. So these are the typical applications. Now you see that the water sports. Okay, if you will wait, then how do you do the water sports? A little heavy will dip you, skiing, and car surfaces. Nowadays, okay, wind seeding. You don't need the wiper at all. Okay, so this can really do this super hydrophobic surface. Okay, so all these applications of super hydrophobics come into life. Okay, from your kitchen to the high-end cars. Okay, everywhere you need the super hydrophobic surface. Okay, now the technology is developing on this direction. And if you look for the physics of it, and this physics comes from the class 10 experiments. Like you take a pool of water on a glass, then put a paper on the top of it and make topside down. You see that though water is very, very heavy, it cannot fall down. So why it is coming? Okay, the kind of surface tension. Okay, similarly, the surface tension experiment people used to do in the class. Okay, in 10+2, in our lab, this kind of surface tension experiment is there. You keep on adding the weight, and still at certain up to a different weight, it cannot dip into the water. It is just float on the surface. So that's why the heavy, even if in the heavy ship, it is floating on the water body in the sea. Okay, those are the kind of application of surface tension, and surface tension play important role to understand that how the force of action at a point, which is if I draw the free body diagram at any point inside, at this point or that point, at the end of the wall or the center of the wall, then we can see that what is the tendency of the liquid to rise up in the narrow tube, which is basically capillary action. Then if you mark that what is the typical forces acting on this, this is my pressure minus 2 times gamma by R. Gamma is my coefficient of surface tension plus rho GH. Then you know that how the surface tension can take the water to the off. This is a surface tension effect. Then you see the perspective automatically having hydro. This is convex. So you can make this surface concave or convex depending on the kind of materials you use. That is the basic density of the material, rho GH. Okay. So depending on that, whether you take a mercury or the water, then in the mercury you will see that in the concave, and in the convex you will see in the case of the water. So this is how the capillary action and surface tension, these two are important parameters to understand the wettability property, or that like hydrophobic or superhydrophobic property. Okay. Then what do we do basically? You look that on the surface, if you have a liquid and solid interface, on the surface of interface of cylinder, there are 3 different kind of forces. Okay. That one is gamma Lg, liquid and gas, and this is liquid, solid and liquid gamma, and gas and solid gamma. So the angle between these will give you that what angle it will make a droplet. Okay. If you do that, the capillary action, then you equate these two gamma R is equal to rho GH at any point. Then instead of a gamma, if you can write that gamma will come rho GH by 2R. Then this is the best, gives us the best way to measure the surface tension. So now, of a pure liquid and solid interface, you know that this is surface tension. Then surface tension between any different kind of liquid or gas, or the solid or liquid, or the solid and gas, the angle is basically defined by the Young's equation. This is the famous Young equation, YSL. This is the surface liquid coefficient, okay, surface tension coefficient, plus y this of cos theta, critical angle of cos theta C is equal to YSG. Okay, so now, then what angle is making? That is important. If the angle is large, that means this surface will become more spherical. If it is very, very small, it is spreading out. Okay, hydrophilic surface. Okay, so then if you look very critically other factors, okay, like if you have then in these equations, let us, there's a other factors are acting, like you have pressure from the top at this point and this point. Let us have a friction of the surface. Okay, all these forces, if you keep on adding and look for the very minutely, then you have other terms are coming off. And then you see that now the Young's formula can change to Laplace formula. Okay, and adding these two, the contact angle you can measure this contact angle of theta, okay, which is the Young's equation, and it is independent of the shape, so whatever shape will be. Then in the compliance, you will find that the force acting in a vertical direction not taken into account here, vertical action. Then theta, cos of theta y is simple like this. Okay, yeah. So then this, whether it has hysteresis or the ideal surface or what kind of surface, what is the contact line of tension, if you consider all these factors together, then it can be complicated and you can minutely tell that what should be the typical action and how you can control the wettability property. That means if I have a hydrophobic surface, the water will be dropped like this. The contact angle you see, if I make like this, is large, more than 90 degrees. Okay, then it pierces to water. I don't want to hear the water. If I love to the water, it will be hydrophilic. I will wet. I love to go and wet myself in the pond or in the rain. But if I don't like it, I'll wear a coat, okay, that like my water coats, and then I'll go to the water and not to be wet. Okay, all the water droplets coming on my body will go away. Okay, so this is how we can work. And if I look critically, that what should be the typical critical angle of the contact angle to make it a hydrophobic. If it is a hydrophobic, it's greater than 90 degrees. it is a hydrophilic, it is less than 90 degrees. So water can spread like this, or the water can become a surface, spherical ball on the surface. If it is more than 150 degrees, we call it a super hydrophobic. Okay, this angle it is super hydrophobic. That means completely one drop is spherical drop is just touching the surface area, touching to the solid is extremely less. Okay, that is a super hydrophobic surface. Okay, then if you look, there are two different kind of mechanism work on this kind of rock surface. One is called Utkal surface, because liquid completely fill the groove of the solid. That means you see it is still a droplet, but it fill the grooves. Okay, then it can roll up that. And similarly, it's a Cassivester state, then the liquid sit on the surface roughness. Okay, it will not fill even if the grooves. Okay, these are two different, even if it is nanostructures, in the nanostructure, we have two different kind of states. If you remember my first slide on this super hydrophobicity, then you see, you might have, you can see that there is a microscopic structure. On the microscopic structure, there are small nanostructures. Okay, these are heavy physical structures. In that structure, if you see, then this will look like this. Okay, then it look or go for the Cassivester state or a Utkal state. Okay, we'll come back to it. So then, how can we make, like the nature has a lot of leaves, how can we make at the lab? Can we make in the lab? In the lab, we can see make these quantum dots or quantum structures on using the ion beams. So it has much advantages, because if we want a particular surface area, want to be wettability surface, and the rest will be looking like that hydrophilic surface. Then we can choose the surface area. Then in large area you can do by ion beams, and other thing is particular, we can control the nanostructures for this. How do you do that? We'll come in the next slides. What do we do? We do a very simple experiment. We take a silicon oxide substrate or a quartz substrate. Then on the surface of this, we deposit some very small nanometer of silicon. And on this, we put a gold. Okay, 6 nanometer. In the next slide, I will tell you why you need a gold at all. If you see, if I put gold on a germanium or on a silicon substrate, then the surface of the gold will look like this. You see that very kind of fractals, or this is a grainy structures. You will find this is as deposited gold. Okay, then this depends on the thickness. How it looks like on the surface, look like a this is 200 nanometer scale. That means depending on how much thin and how the surface is smooth, that will tell you how the color of the golds. Okay, if you go to the goldsmith market and buy some ornament, sometimes you see the deep yellow gold colors, and sometimes you'll see reddish gold. That is rose gold. So that is depends on the how the rough surface of the gold is. Okay, same 24 karat or 18 karat gold you will buy, but if you go to the 18 karat, that means it's not a pure gold. Okay, it has some impurities. Then when the impurity is there, the roughness will be large. Surface roughness will give you the different kind of colors. Okay, yeah. So now, if I anneal at different temperatures for this 361 degree basically the eutectic temperature of gold and germanium, and eutectic temperature of gold and silicon. This is one of the example of gold and germanium. We work on also gold and silicon, it is around 400 degrees centigrade. Then you see this is rough, then surface becomes rougher and rougher, and there is some dots keep on increasing. Okay, nucleation points. These are nucleation points. From there, it started becoming a ball. Now you see, if I keep on increasing my temperature 361 to 500 degrees centigrade, then all these structures become like this. This is a pizza making technology. This is dosa making technology. In the dosa pan, what you do? You put the water, then water will spread around like this in the beginning. At the end, there will be small balls, then it will dry. Then you put your batter on it to make the dosa. So before that, you put some water. Ching. Then the sound will come, then immediately all the water you will put on the dosa plate, okay, one dosa plate where you make your dosa, then it becomes like this, the water will look like this, then it becomes spherical, then it will completely dried out, okay, before you put it. So then, this is like basically de-weighting. This property is called basically de-weighting, okay. This is, this de-weighting, you make the de-weighting, and then at low temperature, you will find this kind of structure. When you go much higher temperature, then the surface becomes, the lot of all this becomes again coagulate, okay? And this process is basically water ripening. This process is water ripening of this de-weighting properties. Then if you go further higher, almost will become hexagonal or spherical completely, okay? And this is on the silicon oxide substrate. As soon as you see, okay, this is the AFM image, that how does it look like on the surface, okay? Instead of a silicon substrate, I also told that in the beginning, we can do the same thing in the quartz substrate. If I do it on the quartz substrate, then you see it's more spherical, okay? That's why in the take a SEM image, you say shadow of each dot. Because if a spherical ball is falling, you put the light on this side, you see the shadow on the other side clearly, okay? So this will give you the more spherical structures. Now, if you see of at different temperature and different time, at 900 degrees, if you change the time, then what will do? You see the interparticle distance. The distance between two nearest neighbors, one is bigger, one is smaller. Now it will become more uniform. When you go to a higher time, then it become more uniform. And the smaller and larger, you will see that two different kind of structure or uniform structures, and that you can do. But this is simple. I take the thin film, put at 900 degrees centigrade, or 800 degrees centigrade, or 700 degrees centigrade. But you remember, when I do this, whole my sample I have to put in the furnace at 900 degrees. That means I don't have any control. Let us, I want a device of 1 centimeter, like chips are basically 1.5 inch by 1.5 inch, okay? This is 1.15 centimeter by 15 mm by 15 mm. Then out of that, only 1 millimeter area, I want that the surface is supposed to be super hydrophobic, and rest will be like that. Okay. Then with the super hydrophobic, I agree it is not, weight is not the only important parameter, there are other electronics property also changes. I'll tell maybe at the end how the electronic property changes. Okay. Then you see, now if I choose a very specific area, how can I do it? So we need some other properties, other technology where you can choose only 1 millimeter area out of this 15 millimeter area, 15 by 15 millimeter area. So for that, I'm giving one of the very important tools where you can choose 1 millimeter area out of all, and that property of 1 millimeter area I can change. So before going to that, let us introduce that what ion beam can do. If ion beam will go into the materials, then it has two different properties. Okay, it can give some surface, and from the material after interaction, something is coming out. If X-ray coming out from the core, knocking out the core electron, the energy is very, very high, then or optical phonons are coming out, optical electrons are coming out, photons are coming out, then we see the PL or electronic property, then those are electronics property. If the interaction of one atom to another atom, okay, the scattering, or some sputtered out some materials from the surface, or some surface from the materials recoiled, those are nuclear in the processes. That means one is the loss, energy loss due to the nuclear energy process, energy loss due to the electronics process. So basically, if you understand these two processes, this is like if you are playing the billiard balls, okay, or carom. If I give my energy to one carom, to the others, then what will happen that this carom board will take one board to the other completely. That means transfer the energy that will go to another. That is, an atom as a whole is replaced. That means the energy is so high, if I have a silicon substrate, some of the silicon will come out from that, and this will be placed there. So if atom as a whole is changing, that is basically called the nuclear energy loss process. But if the energy will be very, very high, hundreds of MeV, 50 of MeV energy, million electron volt energy, then what will happen? it will not get time to interact with the atom as a whole. So what will happen, it interacts the electrons of the atomic cell. Okay, then due to the electronics interaction, and then the vibration in the lattice will happen. When the electron and this vibration will, then the phonons are developed. Phonon, that is lattice vibrations. Then electron phonon interact and give a very high temperature. Due to the very high temperature rise, then you see that changes of the property of the materials. This is basically happens due to the electronic energy loss process. Okay, not even nuclear energy loss process. Okay, so this is very shortly, and that whatever explained phenomenologically, if you see the visualizing it, then what will happen if the incident ion comes, some of the atoms are spotted out, okay, some of the backscattered, some of the reflected, and then you see the energy loss means dE by dx, how much energy loss due to the penetration of that material solid target as two processes, d by dx of n, which is the nuclear process, and dx d by e is the electronic process. So if I give an example, if this some energy of argon will go to in the silicon, then of different energy, then the electronic energy loss will be like this, nuclear energy loss will be like this, the total energy loss will be like this. Okay, so this is how we can identify that what are the different processes happening when ion beam will go into the materials. So now this is the example you see. I told you from the beginning that on the silicon oxide substrate, I put a silicon layers. If I put a silicon layer, then I see the SEM images on the surface. It looks very, very smooth. Then immediately I irradiate the same materials with 1 into 16 ions per centimeter square. In ion beam, I can choose that how many ions per centimeter square I can put. Okay, in it. So I choose 1 into 16 ions per centimeter square, which is very high dose. Then what will happen? The surface doesn't look change much. It's almost like that. But on this next, if I do a gold on the surface of the silicon, then as I told, this is the 50 nanometer scale. I shown that 200 nanometer scale, the surface look like this. Yes, if you see my previous slides here, yeah, this one is like 200 nanometer scale. Then the surface look like this. If I see only 50 nanometer scale, then you can see that this surface is looking like this. This is the gold surface. Then as soon as I put 1 into 69 per centimeter square, as I told that now like dewetting happens in the 900 degrees centigrade, all these particles become like nanodots and rest is silver oxide. That means we create the nanodots similar to the nanoparticles here, okay? Or these are the quantum dots, quantum particle we call, because the dimension is close to the Bohr's radius of that material. Okay, so then we see that this is the peacetime and 1 into 16 happens like this. So this is the difference between if I put the gold on the surface or we don't put on the gold on the surface. So then what this gold do? Gold is a highly thermal conducting material, electrical thermal conducting materials. So as soon as the ion will fall, then it started melting. That ion's energy, 500 keV xenon ions, and at that fluence, it started melting on the surface. So how much temperature rise happened? That temperature for the very short time of 10 to the power minus 12 second, okay, in the picosecond range, okay, the temperature is extremely high. That is more than 900 degrees centigrade. This is around 1500 degrees centigrade. And that temperature, though it is a very fraction of time, immediately it will coagulate and oxidation happens, and then you see the dewetting process is happening. This is called ion beam dewetting. Instead of a thermal dewetting, we call it an ion beam dewetting process. Okay, so then I can tune it. I can make 2 into 50 ions per centimeter square. Large number of gold dots are there. 5 into large more and become smaller. Then 1 into 16, then you see that the distance between these two becomes larger and larger. So now, from the calculation or the theory or from the experiment, you can see that you can control the size, you can control the interparticle distance. So that is one of the parameters when you do the dewetting experiments. So now, the typical count or typical nano silicon particles or gold silicon particles are like 25 nanometer. Here it is 15 nanometers, 18 nanometer. Here the two kind of particles, one is 10 nanometer, one is 25, large number of 25 nanometer nanoparticles along with some 10 nanometer nanoparticles. So these are, we can control over the size, energy, by depending on the energy and the fluence we can do. With this, we see that how much gold remains. Some of the gold is sputting out. Okay, so then you can see that 169 centimeters square, mostly it is NiPi3, gold silicide forms. There are lot, almost there is no gold. Then after you go on higher and higher, gold and silicon both exist. So now these are silicon, gray are silicon, gold are red, okay, and oxygen are green. Because silicon oxide substance. Okay, so now you know that there is still gold silicide forms. So how it is formed? What is the mechanism? As I told you that when iron goes, some of the ions will come out, spotted out, some is mixing together, and some temperature deviating together. So these are three competing process happens. One is some of the gold is spotted out, and some of the silicon come out from that. Then there's an island formed like this. Then out of this island, then this iron will again mixing happens. Means gold and silicon mixed together and make a gold silicide. So new compound also forms. So all these three competing process happens, and you see a different kind of nanostructures are produced. So with this, I can say that this with the depending on the kind of island in the beginning, because in the gold beginning surface you see there are some island kind of fractal structures are there. Okay, there's a gap between two golds. This surface is rough. That rough makes the angle, that at what angle this kind of sputtering happens. So since depending on the angle, the sputtering yield is different. Okay, depending on the angle, the sputtering yield is different. And if the iron will be on the surface like this or this, then more gold will come out. So that's the reason initial substrate, if you see on the gold, then that forms like a different kind of nanostructures. The sinking of the island and finally nanodot formation happens. With this, we can say that we can organize or self-organize synthesis of nanodots, gold silicide or gold nanodots happens. We have a few papers on it, working on this area. Then we look for the hydrophobic surface. Now the surface we can control the interparticle distance and control the particle size. Then we see that if I put a water drop in it, then whether it will go to the Wisconsin-Madison state or Windsor state. So that we have to look for it. Then we do a measurement, then we see that what is the angle between these two. Now, angle becoming more than 90 degrees. Here is the 90 degree. Initially it is hydrophilic, then as you go higher and higher fluence, immediately it go to close to 100. So it is close to superhydrophilic surface. You can go close to superhydrophilic surface and the waterability is there. So now, just imagine, now we have a surface of a glass substrate, that's quartz or glass. On the glass, you produce such kind of nanostructures. You cannot see it by naked eye, but the surface is nanostructures. Then the water drop will fall at little bit angle. Within a fraction of time, all the water will go away. Now, my dashboard of my car, I don't need wipers. As soon as the water drop will fall, it will go immediately cool down. Okay, I don't need a wiper to put it. So that's, and if whatever dust particle is there, okay, that will also clean it. Okay, this is how we can make such kind of structures. Of course, we have a patent on this properties. Okay, working on this. Now, I look what kind of reflection is coming. If I know that if the reflection coming, and this reflection give me the luminescence, photoluminescence. This is a color. As a function of angle, the color changes with the reflection changes. This is UV color. I can change from 354 nanometer to 337 nanometer, and we can go up to even a visible range. That means I put a glass, and these are super hydrophobic surface, but if I look for different angles, it looks colorful. So who is inside, you cannot see it. You can see the color glass on the surface. Okay, because these are reporting with such kind of nanostructures. But inside you can see outside everything, but outside you can see the colors because of the reflections. Okay, so it's a wonderful technology. So you can see that inside in the car, who is sitting, you don't know. The car is super hydrophobic. So from the angle, different angle, you see that the angle, color put glass, you can see from the outside, but this looks at the hydrophobic surface, even if the water will fall, rain will go, then you don't need wiper, everything will go down. Okay, so if I use this not for that purpose. There is some optoelectronics materials. My screen of something, my screen of my mobile. If I change the screen angle, then it will be different colors. Look like. Okay. But as soon as we can see the optical properties of it, okay, the colorful glass, okay, structures you can see. So this is how these quantum dots can help, okay, and the PL you can see, you can tune the PL with very large intensity at 480 nanometers. Okay, then we looked at whether, as I told, that sometimes it is not only gold or silicon nanodots, it has gold silicide. Then to confirm this gold silicide, we have done this XPS, X-ray photoelectron spectroscopy. From here, we see that gold 4F5/2 is there. From here, we confirm this is the gold silicide. That's why I'm telling in the beginning, it's a mixing happens, and due to the mixing of gold and silicon, it forms a gold silicide. Okay. With this, I can summarize that, okay, we can take the bilayers in the beginning. Then with ion beam irradiation, unlike the surface putting in the thermal bath, we put in the ion beams, and controllably with the spatial resolution, we can do the duetting. Due to the duetting, we can have different nanostructures or quantum structures, and this nanostructure or quantum structure can control by the larger or smaller or interparticle distance closure. And depending on the interparticle distance close and high, if I put a water drop, I see the wettability property that whether it is superhydrophobic or lotus normal hydrophobic or hydrophilic surface. When it looks close to the superhydrophobic, it can work as a very good wetting surface where the water cannot wet. So this is basically the lotus leaf effect of ion beam induced or synthesized quantum dots. Okay, I should thank my group. This is one of my group. These two students are master students. They work on this area. These are all my PhD students. These two guys are postdocs. These three are basically postdocs working on this area. And my previous student who are basically most of the like Devi work on this area particularly. Now he is assistant professor at West Bengal University. Nitul is now a scientist. Okay, Mantari joined as assistant professor. Amanandra is also in faculty at IIT Kanpur. And I should thank my collaborator from IUC, Dr. Kanjilal, from Institute of Physics, Dr. Isham, and from Niger, Dr. Karthik Satpathy, Ritik Das, Anamitra, Ashish. They helped me. These two are helping me in experimental different techniques, and Anamitra and Ashish helped me in doing some theory behind it, solving the problems. And I should thank the Niger and DAE for giving the financial support to work on this area. Okay, with this, I thanks for the attention. Now it's open for questions.
Thank you, Professor Sahu. It was indeed a very good informative session. Correlating the hydrophobic property with real applications from kitchen to high-end cars, the presentation actually demonstrated that the development in physics runs parallelly with the development of technology. So we can take questions from the audience. The first question is, the contact angle increases exponentially up to a critical fluence, then it saturates. What are the inferences of it?
Yeah, because as you see that as the ion fluence changes, initially the particles are larger. If the initial particles are larger, that means interparticle distance is small. So when you put a water drop on the surface, both things appear. If I put a water drop and the particles are very distance between two particles is very large, when two nanostructures, then the water can dip inside Wingel states, we can say. So as it becomes closer and closer, okay, then it is a critical interparticle distance where water can sustain properly as a droplet. Okay, like Bhisma Saraswati. You see all the sources, okay, are arranged in such a way, if somebody will sleep on this, then it can still sustain without falling it. Okay, and all the bridge, if you remember the bridge in the civil engineering, okay, all the bridge are on the top of the bolts, okay, they're knife edge and on the top of bridge and surface. So tip surface, okay, and distance, this is an important parameters, okay, then how one can sustain on the top of a tip. Yeah, these are the technology.
Okay. The next question is, why does the morphology evolve under irradiation? Can you please elaborate it again?
Yeah, as I told you that in the beginning, this is the technology, this is the mechanism. Because the mechanism is three different things happening. One is sputtering out. If the angle is like this, then the sputtering more. Then from this island, if from the surface the sputter will be sputtering of the ions, this materials will be sputtered out, then the island becomes smaller and smaller. So morphology changes because as the ion goes, and depending on the initial substrate, in initial the size. Yes, then there are small gaps. When the ion will fall from the gap, it is more preferential sputter out. Then it becomes smaller and smaller. At the same time, the temperature is going high. It started melting for a certain time. So all these three factors, mixing, becoming a compound, the high energy and the fluence, melt it so that it becomes a duetting, and the sputtering. All these three competing processes help to change the morphology.
Thank you. Next question is, what is the range of penetration of the beam?
Yeah, penetration of the beam, you can say that if you see here, it is 500 kV. Okay, so you know that what is the energy initially. Then in the energy, there is somewhere I've written the penetration depth. Okay, the sputtering yield basically. So it depends on the what energy you are taking, what is the material density. Okay, based on that it will penetrate. Yeah, there's a software called SIM. Okay, stopping range in meters. You can calculate it. What is the typical range of the met? I mean, it depends on the energy, how much energy you are putting, and what materials it has. Yes.
The last question is, I'd like to ask, this de-wetting is the process of visualizing the hydrophobic effect?
No.
Then
De-wetting is the process of making the structures spherical. Okay. If you put something in the water, in the temperature, then the material melted, and when melted, it becomes a spherical ball. It is a technology of dosa making technology. Like I told you, if you put water, okay, then heat it, what will happen? The water becomes now, initially it becomes like this, okay, this area, okay, then it becomes a smaller dots, okay, then dot becomes smaller and smaller, that started evaporating. This process is cultivating, means splitting of a particular area to small parts. This process is called wettability. Yeah. Wettability is the property, okay, where you look that what is the contact angle between the surface and a particular box. Okay, that is the property of wettability. Yeah.
Thank you, sir, for your prompt response to the questions. Now, on the behalf of Department of Physics, I would like to thank Professor Raut for sharing his expertise with us. So that's all for the second session of the day 3 of our ongoing FTP. We all will meet again as per the scheduled time, that is at 11 a.m. tomorrow. Thank you.
Thank you very much.